Temperature is one of those words we use every day, yet behind it lies a concept that reaches into the deepest structure of the universe. To say something is warm or cold seems simple, but in physics, temperature is not just a matter of sensation. It is a direct measure of the energy contained in the random motions of atoms and molecules. When a kettle boils on a stove, the water molecules are jostling more violently, colliding with one another at higher speeds. When ice hardens in a freezer, those motions slow, and the vibrations within the crystal lattice shrink almost to stillness. The thermometer is not telling us about some abstract property, but about the very agitation of matter itself. Physicists define temperature as the average kinetic energy of the particles in a system. The faster the molecules or atoms move, the higher the temperature. If they barely move at all, the temperature drops. In gases, this connection is especially clear. The internal energy is carried almost entirely by the kinetic motion of the particles. So doubling the temperature doubles that kinetic energy. In solids and liquids, the picture is more complicated because forces bind the atoms together, but the principle is the same. Temperature is energy distributed among countless microscopic motions. That understanding took centuries to refine. Early natural philosophers thought of heat as a substance, sometimes calling it caloric, that could flow from hot bodies to cold ones. It was not until the 18th and 19th centuries that scientists such as James Joule and Rudolf Clausius showed that heat is not a fluid, but a form of energy transfer. This insight led directly to the laws of thermodynamics, which describe how energy moves, how it changes form, and how it cannot be created or destroyed. Among those laws stands a profound one. There is a lowest possible temperature, a limit beyond which cooling cannot proceed. That limit is absolute zero. Absolute zero is defined as zero on the Kelvin scale, which is minus 273.15 degrees Celsius. At that point, the random motion of particles is reduced to the smallest possible vibrations allowed by the uncertainty principle of quantum mechanics. No matter how advanced our technology, no system can ever be cooled below this fundamental boundary. The Kelvin scale itself was introduced by William Thomson, later known as Lord Kelvin, in the mid-19th century. By establishing a temperature system with an absolute reference point at zero, Kelvin gave physics a universal yardstick. Whether we talk about the heat of a furnace, the chill of liquid nitrogen, or the background temperature of the cosmos, all of it can be placed on the same unambiguous scale. The laws of thermodynamics expand from this definition. The second law explains that energy spontaneously flows from hot objects to cold ones, never the reverse, unless we supply work. That is why refrigerators must consume electricity to pump heat out of their interiors and into the surrounding air. The third law of thermodynamics states that as a system approaches absolute zero, its entropy, or disorder, approaches a minimum. This tells us that reaching absolute zero exactly would require an infinite amount of work, which nature forbids. Together, these principles frame temperature as not just a measure on a thermometer, but as a doorway into the structure of physical law itself. Cryogenics emerged as a science from this theoretical framework. By the late 19th and early 20th centuries, researchers were experimenting with the liquefaction of gases. Oxygen, nitrogen, and hydrogen were successively cooled and condensed, each requiring cleverer methods to extract heat. Heikki Kammerling-Ons achieved the liquefaction of helium in 1911, reaching temperatures only a few degrees above absolute zero. His laboratory work not only demonstrated the possibility of extreme cold, but also revealed superconductivity, a phenomenon where electrical resistance disappears when metals are cooled sufficiently. That discovery showed how temperature governs the behavior of matter in profound and unexpected ways. In astronomy, temperature is equally indispensable. The color of a star reveals the temperature of its surface. Blue stars blaze at tens of thousands of degrees Celsius, while red dwarfs glow faintly at only a few thousand. The internal temperature of stars determines whether hydrogen fuses into helium or whether heavier elements are forged in cataclysmic explosions. Temperature dictates whether interstellar clouds collapse under gravity to form stars or remain diffuse in the void. Even the faint whisper of the universe itself, the cosmic microwave background radiation, is measured as a temperature of about 2.7 Kelvin. In every corner of the cosmos, From the hearts of stars to the near vacuum between galaxies, temperature is a universal currency of energy and motion. When we say something is the coldest place in the universe, we are comparing it against this entire framework. We are measuring not just chill winds or icy surfaces, but the very absence of molecular motion, the dwindling of energy toward the ultimate limit of nature. On Earth, our daily sense of cold is bounded by weather, by atmosphere, and by the warmth rising from beneath our feet. Yet in space, those boundaries are stripped away. Heat cannot be trapped, air cannot circulate, and radiation alone determines the exchange of energy. The cold of the cosmos is of a different order entirely, one that dwarfs the most extreme winters known on our planet. This sets the stage for a journey that begins with what we know on Earth and extends outward into the vastness beyond. From the coldest stations in Antarctica to the frozen shadows of distant moons, and finally, to interstellar clouds and dying stars, we will follow temperature down into the deepest wells of natural cold. Along the way, we will find not only physical limits, but also glimpses of the ultimate fate of the universe. Temperature is not merely a number on a scale, it is a story of energy, motion, and destiny. The notion of absolute zero might appear to be an abstract construct, yet it has very real consequences. The closer a system comes to that limit, the more strange and counterintuitive its behavior becomes. At ordinary temperatures, atoms and molecules are in constant agitation, colliding and rebounding, exchanging energy in chaotic fashion. As the temperature lowers, the motions slow, and quantum effects begin to dominate. Instead of behaving like individual particles, the constituents of matter can merge into collective states. This is the domain of Bose-Einstein condensates and superfluids, where an entire collection of atoms acts in unison, like a single quantum entity spread out over macroscopic space. These discoveries, made in the 20th and 21st centuries, confirm the insight that temperature is not merely about comfort or survival, but about the very regime in which the laws of physics operate. To appreciate how deeply temperature is woven into our universe, consider the everyday thermometer. The mercury thermometer, first devised in the 18th century, relies on the expansion and contraction of liquid mercury as it warms or cools. The scale is marked to give us numbers, but behind those numbers lies a precise correspondence with the kinetic energy of molecules. Later technologies, such as digital thermistors or infrared sensors, refine the measurement, yet the principle remains the same. When astronomers speak of the surface temperature of a star thousands of light years away, they are extending this same principle into the cosmic realm. The starlight spectrum reveals how atoms in that distant furnace are vibrating and radiating, and from that signature, we can read temperature across unimaginable distances. The importance of temperature also reaches into cosmology. When the universe first emerged from the Big Bang nearly 14 billion years ago, it was in a state of extreme heat, far hotter than any star we see today. Temperatures in the first fraction of a second soared to trillions of degrees Celsius, high enough that matter itself could not exist as atoms or even as protons and neutrons. As the cosmos expanded, it cooled, and in that cooling sequence, particles combined, atoms formed, and eventually, galaxies and stars appeared. In this way, temperature became not only a measure of present conditions, but also a timeline of cosmic history. Every stage of structure in the universe corresponds to a particular cooling threshold. The Kelvin scale is uniquely suited to express this history. At the blazing core of stars, where fusion occurs, temperatures are counted in tens of millions of Kelvin. At the other extreme, the faint cosmic microwave background glows at only 2.7 Kelvin. The span from absolute zero to stellar furnaces is immense, yet the same scale covers it all without ambiguity. It is this universality that allows us to speak with confidence about the temperature of a nebula light years away, or the chill of interstellar space that no human has ever touched. The Kelvin scale bridges the laboratory and the cosmos. The subtlety of temperature emerges as well when we examine entropy. Entropy is a measure of how many microscopic configurations correspond to a given macroscopic state. A block of ice has lower entropy than the same amount of liquid water because its molecules are locked into a more ordered lattice. The second law of thermodynamics states that in an isolated system, entropy tends to increase, And in practice, this is what we experience as the irreversibility of processes. Heat flows from hot to cold, not the reverse. A cup of coffee left on a table cools down, but it never spontaneously heats up. Temperature is the quantity that mediates this flow. It is the gradient in temperature that drives the inexorable march of entropy forward. Understanding this connection clarifies why temperature is so central in astrophysics. In the heart of a collapsing molecular cloud, gravity pulls matter inward, converting potential energy into kinetic energy, which manifests as rising temperature. That heat resists the collapse until it reaches a threshold where nuclear fusion ignites. From that point onward, the balance between gravity and thermal pressure determines the entire life cycle of the star. Without temperature, there would be no limit to gravitational collapse, and stars would never stabilize. Instead, they would plunge straight into black holes. The fact that stars shine for billions of years is testimony to the delicate balance maintained by thermal processes. Even the emptiness between galaxies is not truly cold in the everyday sense, because it is permeated by the cosmic microwave background. This radiation, a relic of the primordial fireball, sets a temperature floor throughout space. When we measure its faint glow at 2.7 Kelvin, we are sensing the embers of creation itself. Every atom, every dust grain, every molecule in the universe is bathed in this background, and it defines the baseline of thermal reality. That is why when astronomers report the discovery of regions colder than the cosmic microwave background, it is such a remarkable claim. It means that under specific conditions, nature can contrive to slip below what seems like a universal minimum. The conceptual journey from the ordinary thermometer to the cosmic temperature scale reveals the power of scientific abstraction. The same laws that explain why ice melts or why water boils also explain the birth of stars and the cooling of the universe. Each degree, whether in Celsius or Kelvin, corresponds to an increment in the microscopic agitation of particles, and through that connection we gain a bridge from our senses to the deep physics of reality. When explorers at the South Pole endure temperatures of -80 degrees Celsius, they are experiencing molecules slowed to a fraction of their typical vigor. When astronomers describe the Boomerang Nebula at 1 Kelvin, they are describing a place where motion itself has nearly ebbed to nothing, where the universe has created a natural freezer more efficient than any we can build on Earth. The precision with which scientists can now measure and control temperature is a triumph of modern physics. Lasers tuned to exact frequencies can nudge atoms into lower and lower energy states. Magnetic fields can trap them with delicate precision. These laboratory feats have allowed us to approach billionths of a Kelvin, proving that the theoretical constructs of absolute zero and the Kelvin scale are not just philosophical musings, but practical guides. They let us construct machines, probe quantum effects, and measure the faint afterglow of the universe itself. In all these ways, temperature is revealed as a central axis of scientific understanding. As we deepen this exploration, the contrast between earthly cold and cosmic cold will become ever more vivid. Our planet, wrapped in atmosphere and warmed by internal heat, has a narrow range compared to the abyss beyond. The chill of Antarctica is severe by human standards, yet it is still hundreds of degrees above absolute zero. To find the true limits, we must look beyond the sky, into places where starlight barely reaches, and matter itself expands into oblivion. The story of cold in the universe is a story of how low energy can go, of how close nature can approach the absolute boundary of motion. The path toward understanding temperature also reshaped how humanity thinks about time itself. Before the modern era, people reckoned time with the motions of the sun, the rhythms of the moon, or the turning of the seasons. But the second law of thermodynamics introduced the idea that time has a preferred direction. Because entropy increases as heat flows from hot to cold, the universe carries an arrow of time embedded within it. A broken cup does not leap back together. A cloud of gas does not spontaneously contract and heat unless energy is exchanged. Temperature, entropy, and the passage of time are intertwined in a way that makes our experience of past, present, and future more than a human perception. They are written into the physics of the cosmos. This perspective reveals why absolute zero is unattainable. To reach it, one would have to extract every last trace of energy from a system. That would mean forcing entropy to stop increasing, which the laws of thermodynamics forbid. Even in the emptiness of intergalactic space, where densities are measured in a handful of atoms per cubic meter, there remains some vibration, some photon, some faint whisper of energy that keeps temperature above zero. The fact that we can get as close as a fraction of a billionth of a Kelvin in laboratory conditions is a triumph, but the final step is forever out of reach. In this way, absolute zero is like the horizon of a black hole. It is a boundary we can approach but never cross. When scientists began to map the temperatures of the cosmos, they realized that these principles apply everywhere. A planet like Mercury swings from scorching heat to deep cold depending on whether it faces the sun or not, because without a thick atmosphere to distribute energy, the surface undergoes extremes. Jupiter's moon Europa holds a frigid, icy crust, yet tidal forces from its giant parent world warm its interior enough to sustain a possible subsurface ocean. These examples illustrate that temperature is never just a number. It is a balance between sources of heat and mechanisms of cooling, between radiation from stars, conduction through matter, and the endless expansion of space itself. The same rules govern every world and every nebula. The study of temperature also shapes how astronomers think about habitability. The so-called habitable zone around a star is defined by where liquid water can exist. If a planet is too close, water evaporates. If it is too far, water freezes solid. This balance is again determined by temperature, which in turn depends on the star's luminosity, the planet's atmosphere, and its distance. When we search for life beyond Earth, we are in fact searching for the right range of temperature. It is remarkable that something as simple as average kinetic energy of molecules can hold the key to the emergence of biology and perhaps intelligence. From the everyday to the cosmic, temperature unites experiences that seem utterly different. The warmth of a hearth fire and the glow of a distant quasar are described on the same scale. The chill of liquid helium in a laboratory and the background radiation left over from the Big Bang are measured by the same principle. This unity is part of what makes physics so powerful. It reduces diverse phenomena to a shared language, allowing us to connect our senses with the deep machinery of the universe. To say that the Boomerang Nebula is colder than the background of space itself is meaningful only because we have this common scale. Without it, such a statement would be little more than metaphor. The journey through these concepts has prepared us to step outward. We have traced temperature from its definition as microscopic energy through the historical development of thermodynamics into the laboratories of cryogenics and the hearts of stars. We have seen how absolute zero defines a lower bound and how entropy ensures that temperature has consequences for the flow of time. We have touched on how cold governs planetary environments, the search for life, and the balance of cosmic history. All of this is the groundwork for the central question: where in the universe is the coldest place of all? The answer requires leaving the comfort of our planet and traveling beyond the protective shield of atmosphere. It requires comparing the chill of Earth's poles with the void of interstellar space, weighing the faint background radiation of the universe against the shadowed recesses of nebulae, and finally confronting an object so strange that it challenges our expectations of what nature allows. That journey begins with Earth itself. Before we can measure the cold of space, we must first consider the coldest places on our own world, where explorers and instruments have pushed the boundaries of human endurance. In doing so, we will establish a baseline, a reference against which the vastness beyond can be measured. To understand the scale of cosmic cold, it is useful to begin with the coldest places we know on Earth. For all the power of physics, for all the vastness of the cosmos, our own planet remains the immediate laboratory where temperature is tested, measured, and endured. Earth is not the coldest place in the universe by any measure, yet the extremes recorded here stretch human limits and provide the first step on a ladder that leads to interstellar cold. In Antarctica, on windswept plateaus thousands of meters above sea level, we encounter some of the harshest natural conditions on the surface of our world. The Soviet Vostok Station, situated near the center of the East Antarctic ice sheet, has long been known as a site of unparalleled cold. In July 1983, meteorologists measured a temperature of -89.2 degrees Celsius, the lowest reliably recorded on the surface of Earth. At such a temperature, steel becomes brittle, exposed skin freezes in moments, and the air itself seems heavy and stinging. Breathing requires care, for moisture in the lungs can crystallize. Life in this place is reduced to survival, and survival depends on technology. Heated shelters, thick insulation, and constant monitoring are necessary. The human body is simply not built for such extremes. Later, satellite observations revealed even colder spots nearby, at sites such as Dome Fuji and Dome Argus, which reach higher altitudes on the Antarctic plateau. In 2013, data from NASA's satellites identified surface temperatures below -93 degrees Celsius in small, isolated hollows. These conditions occur on clear winter nights, when the thin air allows infrared radiation to escape directly into space. Cold air pools into the depressions, and without wind to stir it, the temperatures plunge. Though these satellite records surpass the Vostok measurement, they represent fleeting surface readings rather than long-term averages. Still, they mark the lower boundary of what our planet's climate can produce, unaided. Why can Earth not get colder still? The answer lies in the insulating effect of atmosphere and the steady leakage of geothermal heat from the planet's interior. Even at the poles, where the sun provides little energy in winter and where long nights stretch for months, there remains a constant trickle of warmth from below. Radioactive decay in the mantle and residual heat from Earth's formation maintain a background flow that seeps through the crust. Without this contribution, surface temperatures could fall lower, but the planet cannot shed this heat entirely. Likewise, the blanket of air that surrounds us prevents radiation from escaping too quickly. Molecules of nitrogen, oxygen, and trace greenhouse gases scatter and absorb energy, slowing the descent into deeper cold. This limitation highlights the contrast with outer space. In the absence of atmosphere, cooling proceeds differently. On Earth, convection and conduction move heat between surfaces and the surrounding air or soil. In space, where air is absent, the only way for an object to lose heat is by radiating infrared light into the void. The process is slower than one might imagine because radiation is far less efficient than conduction or convection. A human body exposed to the vacuum of space, though unprotected against pressure and radiation, would not freeze instantly. Instead, body heat would radiate away gradually, and it might take minutes before temperatures dropped dangerously. Cold in space is not the immediate frost of an Antarctic night, but the long, inexorable bleeding of heat into emptiness. When astronomers consider the cold of planets and moons, they apply these principles. Pluto, orbiting on the edge of the solar system, averages a surface temperature near -225 degrees Celsius. Triton, Neptune's largest moon, reaches similar conditions, with nitrogen frost and geysers of sublimating ice. Europa, one of Jupiter's icy moons, has a surface temperature around -160 degrees Celsius. These are places where water is as hard as rock and where sunlight provides barely a whisper of warmth. Yet even here the story is nuanced. Beneath Europa's frozen crust, tidal forces stir its interior and may keep oceans liquid. Cold defines the surface, but deeper layers may hide different thermal regimes. The comparison between Earth's coldest deserts and these distant worlds is instructive. Antarctica's Dome Argus at -93 degrees Celsius is unthinkably severe by human standards. Yet it is still warmer by more than 100 degrees than the ice plains of Triton. What limits us on Earth is not the absence of sunlight alone, but the presence of an atmosphere and internal heat. Other worlds, lacking such protection or orbiting far from the sun, can plunge far lower. And still, even Pluto and Triton are not the coldest. The void between the stars, untouched by planetary geology or solar radiation, sinks closer to the true floor set by the universe itself. Here we begin to sense the scale of the journey. The coldest valleys on Earth are a prelude, a mere foothold on a vast descent. Our planet, for all its extremes, remains wrapped in warmth compared to the interstellar medium. The path downward continues beyond the reach of any expedition, into places where no human has walked, and where even spacecraft struggle to detect the faintest signals. The chill of Antarctica, severe as it is, pales beside the quiet cold of space. Antarctica has long been the ultimate testing ground for human endurance against cold, but even there, the numbers fall short of what we encounter when we look beyond our world. The very fact that Vostok Station and Dome Argus remain only a few tens of degrees below 100 degrees Celsius illustrates the limits of Earth. These places represent the boundary where atmosphere, latitude, and elevation conspire to produce the most intense natural cold available on the surface. Yet if we place them side by side with the outer solar system, the contrast becomes staggering. It is not a matter of a few degrees, but of entire orders of magnitude closer to absolute zero. Consider Pluto, a dwarf planet orbiting in the Kuiper Belt, nearly 6 billion kilometers from the Sun at its farthest point. Pluto receives less than 1,000th of the sunlight that Earth enjoys. Its tenuous atmosphere, composed mainly of nitrogen, with traces of methane and carbon monoxide, collapses and freezes onto the surface as frost during its long winter. The average surface temperature hovers around -225 degrees Celsius, so low that nitrogen itself becomes a solid. When astronomers captured images of Pluto through the New Horizons mission in 2015, they revealed a world where vast plains of nitrogen ice stretch across the surface, sculpted by processes utterly alien to our temperate world. For comparison, this is more than 130 degrees colder than the lowest measured temperature in Antarctica. Triton, Neptune's largest moon, is even more remarkable. Discovered in 1846 by William Lassell, Triton circles Neptune in a retrograde orbit, indicating that it was likely captured from the Kuiper Belt. Its surface temperature is about -235 degrees Celsius, making it one of the coldest known bodies in the solar system. Despite this, Triton is geologically active. Voyager 2, which flew past in 1989, observed geysers erupting from beneath the frozen crust, spraying nitrogen gas and dust several kilometers into the sky. These geysers are driven not by heat in the sense we experience it on Earth, but by subtle warming from sunlight and perhaps internal tidal stresses, enough to sublimate nitrogen just below the surface and create pressure that escapes violently into the near vacuum. The paradox of a frozen yet active world underscores that cold does not mean inert, but rather defines a different set of physical processes. Other icy moons paint similar pictures. Europa, orbiting Jupiter, maintains an average surface temperature near -160 degrees Celsius. Its crust of water ice, scarred with cracks and ridges, conceals a hidden ocean, warmed by tidal heating. Enceladus, a small moon of Saturn, is only slightly warmer, yet it jets plumes of water vapor and ice particles from fissures near its south pole. In both cases, the bitter cold of the surface coexists with the possibility of habitable environments beneath. Temperature alone does not dictate habitability, but it sets the stage. The surface may be frozen solid, but warmth from below can carve out niches of liquid water, a reminder that the cosmos is more varied than surface impressions suggest. When we compare these outer solar system bodies with Earth's coldest points, the contrast is dramatic. The -93 degrees Celsius observed at Dome Argus seems almost temperate beside -225 degrees Celsius on Pluto or -235 degrees Celsius on Triton. And still, these worlds are not at the ultimate limit. The cold of outer space itself, away from planetary surfaces and atmospheres, is even more profound. The absence of any medium for conduction or convection means that the only way for objects to cool is by radiating energy away as infrared light. Once they do so, they are left to drift at temperatures approaching the cosmic background, the universal bath left over from the Big Bang. Spacecraft traveling through the outer solar system illustrate this reality. The Voyager probes, launched in 1977, are now more than 20 billion kilometers from Earth, traversing the interstellar boundary. Their instruments must contend not only with the near vacuum, but also with the ambient temperature of space itself, which is only a few degrees above absolute zero. The electronic systems aboard these probes are kept alive not by environmental heat but by nuclear power sources that generate electricity and warmth. Without this artificial support, the probes would succumb quickly to the pervasive cold. This is a stark difference from Earth, where even in Antarctica, the surrounding air provides some thermal buffer. The concept of cold on Earth, then, must always be understood relative to our environment. The atmosphere prevents heat from radiating away too quickly. The planet's core ensures a baseline of warmth that seeps upward. Even the oceans, vast reservoirs of thermal inertia, stabilize climate and prevent wild fluctuations. It is only in isolated basins on the Antarctic plateau, under clear skies and still winds, that nature can achieve its coldest extremes. Yet, compared to space, these are modest. The void beyond our atmosphere is an unrelenting freezer, where temperature is defined not by weather, but by the slow radiation of energy into infinity. In this way, Earth's coldest environments serve as a training ground for the imagination. They give us numbers and experiences we can grasp. -89 at Vostok, -93 at Dome Argus. They teach us what extreme cold feels like to human senses, how it seizes breath, freezes machinery, and challenges survival. But they also highlight how narrow our perspective is. The Antarctic plateau is still hundreds of degrees above the surfaces of Pluto and Triton, and those surfaces in turn are still warmer than the emptiness of interstellar space. To understand the true scale of cold, we must keep climbing down the ladder, step by step, from our planet to the solar system and beyond. When we extend our attention beyond planets and moons, the scale of cold grows more profound still. Between the stars lies the interstellar medium, a sparse mixture of gas and dust stretched across immense gulfs of space. Unlike Antarctica, where dense air and ice keep temperatures above -100 degrees Celsius, the interstellar medium is so thin that atoms are separated by distances of many centimeters, sometimes meters. In such conditions, the very concept of temperature must be approached with care. Temperature still corresponds to the average kinetic energy of particles, yet when the density is so low that collisions are rare, the meaning becomes more abstract. Nevertheless, astronomers measure these regions and find that their temperatures range from thousands of Kelvin in ionized clouds to only a few tens of Kelvin in dense molecular regions. Compared to Earth, the latter are astonishingly cold, hovering near -260 degrees Celsius. The fact that interstellar space cools so effectively arises from the absence of atmosphere and the absence of nearby stars. A grain of dust drifting far from any stellar influence has no source of heat other than the faint cosmic microwave background radiation. That radiation itself represents a universal floor of temperature, about 2.7 Kelvin, or -270 degrees Celsius. This is colder by far than any place on Earth, and it permeates every corner of the observable universe. In effect, the cosmos has a baseline temperature set not by weather or planetary dynamics, but by its own origin in the Big Bang. When researchers record this number, they are measuring the cooled embers of creation itself. The comparison between this background and Earth's extremes is stark. At Vostok Station, the cold bites fiercely, yet it is still more than 180 degrees warmer than the background of space. A difference of that magnitude is almost beyond human intuition. To walk outside at Vostok without protection is lethal, yet to drift unprotected in interstellar space would expose one to a cold that dwarfs even that danger. The body, radiating heat, would eventually cool toward the universal floor, losing energy not to an atmosphere, but to the emptiness itself. Survival would be impossible, not because the cold is actively freezing as on Earth, but because the lack of heat exchange, except by radiation, means that one can never replenish what is lost. This realization transforms our perspective. Cold is not simply a property of place or climate. It is an outcome of energy balance, of the interplay between sources of heat and the efficiency of cooling. On Earth, the balance is constrained by atmosphere and geothermal activity. In the solar system, it is determined by distance from the sun and the ability of bodies to retain heat. In interstellar space, it is governed by radiation alone, which drags temperatures down close to absolute zero. This hierarchy illustrates why Antarctica, despite its brutal reputation, is a warm cradle compared to the natural conditions of space. Earth cannot compete with the cosmos in a contest of cold. And yet, the story does not stop here. Even within this framework, there exist exceptions. Certain nebulae, shielded from background radiation, can cool below the cosmic microwave background, and the Boomerang Nebula reaches astonishingly close to 1 Kelvin, colder than the background itself. This extraordinary fact will emerge later in our journey. For now, it is enough to recognize that Earth provides only the introduction. The frozen plateaus of Antarctica and the icy surfaces of Pluto or Triton are waypoints along a descent that leads far lower, into conditions that defy our direct experience. The transition from Earth to space also highlights how our methods of measurement evolve. Thermometers and satellites serve us on our planet, while spacecraft, telescopes, and radio arrays are needed for the void beyond. To speak of 2.7 Kelvin across the cosmos is not speculation, but the result of decades of careful observation, from the discovery of the cosmic microwave background in 1965 to the precision measurements of COBE, WMAP, and Planck. These instruments extend the same principle that records -89 degrees in Antarctica into the domain of galaxies and nebulae. Cold is a universal concept, whether measured in a frozen hollow or in the faint glow of microwaves that bathe all creation. Standing at the threshold of this understanding, we see clearly that Earth's coldest environments are stepping stones. They ground us, they test us, they remind us of our vulnerability, but they also point outward. The Antarctic plateau whispers of conditions that exist more fully beyond the sky. The comparison reveals scale. Earth is severe, yet space is harsher. The planet is hostile in places, yet the cosmos is indifferent everywhere. To continue downward toward the coldest place in the universe, we must leave the comforting boundaries of our world and enter the background itself, the universal chill that defines the temperature of space. When we step beyond planets and moons, beyond even the frozen deserts of Antarctica, we encounter a new kind of cold. It is not the cold of weather, nor of seasonal extremes, but of the universe itself. For in the silence between the galaxies there exists a faint radiation that fills all of space, a relic left over from the birth of the cosmos. This is the cosmic microwave background, often shortened to CMB, and its temperature of 2.7 Kelvin defines the baseline for the universe. To understand this radiation is to understand not only the limits of natural cold, but also the origin and history of everything we see. The story begins nearly 14 billion years ago with the Big Bang. In its earliest fraction of a second, the universe was a searing furnace, hotter than any star, filled with a plasma of particles and radiation. At those temperatures, trillions of degrees Celsius, matter could not form stable atoms. Protons, neutrons, and electrons swirled in a dense soup of energy, colliding constantly with photons. The universe was opaque, a glowing fog where light could not travel freely. As the cosmos expanded, it cooled, and after about 380,000 years, a critical threshold was reached. Electrons combined with nuclei to form neutral hydrogen atoms, and at that moment, light was released. Photons, no longer scattered at every turn, began their long journey across space. That ancient light is what we now detect as the cosmic microwave background. Originally, this radiation was blindingly bright, at a temperature of thousands of Kelvin. But over billions of years of expansion, the wavelengths of the photons stretched, and the temperature fell. Today, that same radiation has cooled to just 2.7 Kelvin, corresponding to microwave frequencies invisible to the eye, but detectable with sensitive instruments. The astonishing part is its uniformity. No matter where we look in the sky, in every direction, we see nearly the same temperature. It is as if the universe itself has a background hum, a faint echo of its beginning, setting the floor of thermal reality everywhere we go. The discovery of the cosmic microwave background in 1965 was one of the great milestones of modern science. Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs, were testing a large horn antenna when they encountered a persistent noise. At first, they suspected interference, perhaps from pigeon droppings on the equipment, but cleaning the antenna did not solve the problem. The signal persisted, steady and isotropic, coming from every part of the sky. At the same time, theoretical physicists working on models of the Big Bang had predicted just such a relic radiation. The realization was immediate. What Penzias and Wilson had found was nothing less than the afterglow of creation itself. For this discovery, they received the Nobel Prize, and cosmology was forever changed. The measurement of the CMB soon became a central tool in cosmology. Satellites such as the Cosmic Background Explorer, or COBE, launched in 1989, refined the picture. COBE confirmed that the radiation matched an almost perfect blackbody spectrum, the theoretical shape of light, emitted by a body at a uniform temperature. The match was so precise that it remains one of the most convincing proofs of the Big Bang. Later missions pushed further. The Wilkinson Microwave Anisotropy Probe, or WMAP, mapped the small fluctuations in temperature across the sky, variations of only millionths of a Kelvin. These tiny differences revealed the seeds of cosmic structure, the faint imprints of regions where matter was slightly denser, regions that would grow into galaxies and clusters. Most recently, the Planck satellite, launched by the European Space Agency, produced the most detailed map yet, showing the fine structure of the universe's first light with exquisite resolution. The CMB is therefore not just a background hum, but a snapshot of the infant universe. It tells us how matter was distributed, how fast the cosmos was expanding, and even the age of the universe itself. Its temperature of 2.7 Kelvin is not arbitrary, but the natural consequence of billions of years of cosmic cooling. Every atom, every star, and every galaxy exists within this sea of faint microwave photons. To measure cold in the universe is to measure against this universal baseline. No region, no matter how remote, can escape it. The CMB is everywhere, the floor upon which all thermal processes unfold. The cosmic microwave background is remarkable not only for its presence, but also for its precision. Imagine a canvas stretched across the entire sky, painted in the faintest glow of microwaves, each patch nearly identical in temperature. Sensitive instruments reveal variations of only a few parts in 100,000. This near uniformity tells us that the universe, at the time of recombination, was astonishingly smooth. Yet the tiny fluctuations embedded in that smoothness carried the seeds of everything to come. Regions just a fraction denser than their surroundings would, under the influence of gravity, grow into galaxies, clusters, and filaments, while slightly underdense regions would become the vast cosmic voids we now observe. In this way, the subtle ripples in the temperature of the CMB are the blueprint of cosmic structure. For decades, cosmologists have refined the measurement of these fluctuations. The COBE satellite first detected them in 1992, revealing a blotchy map of hot and cold spots that matched predictions from the theory of cosmic inflation. Inflation posits that in the earliest instant after the Big Bang, the universe expanded faster than light, smoothing out irregularities while magnifying tiny quantum fluctuations into macroscopic seeds. WMAP, in the early 2000s, sharpened this image, producing maps that displayed the power spectrum of these fluctuations, a statistical pattern that could be compared directly with theoretical models. Planck, launched in 2009, delivered the most precise measurements to date, confirming the predictions of the Big Bang and providing tight constraints on parameters such as the density of dark matter, the density of dark energy, and the overall curvature of the universe. The uniform temperature of 2.7 Kelvin is more than just a number. It defines a floor beneath which most natural environments cannot fall. Every particle of dust, every gas cloud, every comet drifting in the void is bathed in this radiation. Left alone long enough, any object will radiate away its internal heat until it reaches equilibrium with the CMB. This means that in the absence of active heating, cosmic bodies settle near this temperature. It is why the vast majority of intergalactic space hovers just a few degrees above absolute zero, not far above the CMB's value. In essence, the CMB sets the thermostat for the universe. The significance of this becomes clearer when we compare it to Earth. The coldest temperatures recorded in Antarctica, or even on Pluto or Triton, are hundreds of degrees warmer than the CMB. If we could place a block of Antarctic ice in deep space, it would not remain at minus 90 degrees Celsius. Instead, it would continue radiating energy until it reached equilibrium with the 2.7 Kelvin background. In effect, the cosmic microwave background is the true backdrop against which all other temperatures must be measured. It is not just colder than Antarctica, it is colder than the surfaces of most known planets and moons, setting a universal reference. This floor of temperature also explains why discoveries of regions colder than the CMB attract such attention. The background is supposed to be the minimum, the unavoidable radiation that permeates everything. To find natural environments that dip below it requires special conditions, usually involving rapid expansion or shielding from background photons. The Boomerang Nebula is one such case, a unique preplanetary nebula whose expanding gas cools adiabatically to near 1 Kelvin, colder than the background itself. But before we explore that, it is important to appreciate how extraordinary the CMB is. It is not simply the residue of the Big Bang, but a constant reminder that the universe is still cooling, still stretching, still evolving. The measurement of the CMB has also allowed cosmologists to determine the age of the universe with remarkable precision. By analyzing the detailed fluctuations, Planck estimated the age to be 13.8 billion years, with an uncertainty of less than 1%. The temperature of the CMB encodes not only when the first atoms formed, but also the subsequent expansion history. It is as if the universe carries within it a fossil record, not of bones or shells, but of light itself, a frozen imprint of conditions long vanished. Every photon we detect from the CMB has been traveling for nearly 14 billion years, only now reaching our detectors after an uninterrupted journey across space and time. Thus, when we talk about the cold of the CMB, we are not speaking metaphorically. We are speaking of a measurable, physical temperature, one that sets the baseline for the cosmos. To grasp its importance is to realize that the universe has a memory written in the faint microwaves that still bathe us. That memory defines the cold against which everything else must be compared. The cosmic microwave background is everywhere, yet it is not absolute in the sense of being unalterable. Matter can interact with it, absorb it, or shield against it. Dense molecular clouds, for instance, provide regions where the radiation field is suppressed. These clouds are the dark nebulae astronomers observe through radio and millimeter wavelengths, vast assemblages of hydrogen molecules, helium, and traces of heavier elements. Within them, dust grains absorb starlight and re-emit it at longer wavelengths, while the gas inside cools to temperatures as low as 10 Kelvin. These clouds are so opaque that they block background radiation from penetrating their densest cores. In those hidden recesses, shielded from the CMB, temperatures can drop slightly below the average cosmic value, though never to zero. The very fact that they can dip below 2.7 Kelvin shows that conditions in the universe are complex, not uniform. Astronomers use sophisticated techniques to measure such low temperatures. Because molecular hydrogen is nearly invisible at these energies, they rely on tracer molecules, such as carbon monoxide, ammonia, or formaldehyde. By observing the rotational transitions of these molecules at millimeter and submillimeter wavelengths, scientists can infer the thermal state of the gas. Radio telescopes like those at the Atacama Large Millimeter Array, or ALMA, are exquisitely sensitive to this radiation, able to detect faint signals from regions thousands of light-years away. The spectra of these molecules reveal whether the gas is in equilibrium with the CMB or cooler, and by how much. Such studies confirm that molecular clouds can harbor the coldest reservoirs of matter in the galaxy, precursors to star formation hidden within their icy depths. The interplay between the CMB and these clouds is profound. The radiation provides a heating floor, while cooling mechanisms such as emission from dust and molecular lines allow the temperature to sink further. The balance between these processes shapes whether a cloud collapses under its own gravity. If the gas is too warm, pressure resists collapse. If it is cool enough, gravity wins and new stars ignite. Thus, the story of cold is not merely about extremes, but about creation itself. Without the cooling that brings gas to 10 Kelvin, stars like the Sun could never form. In a sense, our very existence depends on the ability of matter to radiate heat, and to slide downward toward lower and lower temperatures, brushing against the limit set by the cosmic background. Yet for all their importance, molecular clouds remain warmer than the most extreme example we know. The CMB defines the floor for much of the cosmos, and clouds can sink close to it, but only under extraordinary conditions can nature go further. The Boomerang Nebula, as we will see, manages to cool itself to about 1 Kelvin, colder than the background itself, through a mechanism of rapid expansion. This is not the ordinary cooling of a shielded gas, but the result of a dying star ejecting material at tremendous speed. Before we arrive there, however, it is worth reflecting on what the CMB represents. It is the faint whisper of the universe's first light, stretched across billions of years, bathing every particle in its gentle chill. It is both a relic of unimaginable heat and the standard of unimaginable cold. The CMB is a paradox in that sense. It is the remnant of fire, yet it defines the cold. It is ancient light, yet it sets the present condition of the cosmos. It is uniform, yet it contains the seeds of structure. For anyone seeking the coldest places in the universe, it is the reference point, the foundation upon which all comparisons must be made. Antarctica, Pluto, Triton, even the void between galaxies, all are warmer than this 2.7 Kelvin bath. To find something colder, one must search for extraordinary cosmic laboratories, rare environments where expansion or isolation allows matter to slip beneath the universal floor. Those places exist, and they teach us not only about cold, but about the life cycle of stars and the ultimate destiny of the cosmos. Between the stars lies an ocean of invisibility, a place where matter exists so thinly that it is almost a vacuum, and yet, in its collective mass, it outweighs all the stars put together. This is the interstellar medium, a tenuous mixture of gas, plasma, and dust that stretches across the Milky Way. Though sparse, it is the raw material of galaxies, the reservoir from which new stars and planets are born. Within this medium, vast regions cool to extraordinary depths, forming clouds that shield themselves from radiation and sink toward the limits imposed by the cosmos. These are the cold reservoirs of space, and in their hidden cores, temperatures fall to values that would seem impossible by earthly standards. The interstellar medium is not uniform. It consists of phases, each with its own density and temperature. There is the hot, ionized medium, filling large cavities with gas heated by supernova explosions, glowing at millions of Kelvin. There are warm, neutral, and ionized components, with temperatures of thousands of Kelvin, filling much of the volume of the galaxy. And then there are the cold, neutral, medium, and molecular clouds, the densest and most frigid regions, where temperatures can plunge to 10 or even as low as 5 Kelvin. It is within these molecular clouds that stars form, and the story of cold in the universe cannot be told without them. Molecular clouds are immense, often spanning tens or hundreds of light years. They contain mostly molecular hydrogen, H2, though it is notoriously difficult to detect directly. Instead, astronomers use tracer molecules, especially carbon monoxide, whose rotational transitions emit radiation at millimeter wavelengths. By mapping these emissions, telescopes reveal the intricate structure of the clouds, filaments, knots, and dense cores, where gravity is gathering matter. The Horsehead Nebula in Orion is one of the most iconic, a dark silhouette against the glowing background of ionized hydrogen, its dense cold gas blocking starlight. Another famous example is Barnard 68, a small dark nebula in the constellation Ophiuchus, so opaque that it blots out background stars entirely, a void in the sky that is not empty, but full of unseen cold. The physics of cooling in these clouds is subtle. Atoms and molecules collide, and in doing so they excite rotational or vibrational states. When these states decay, they emit photons that escape, carrying energy away. Dust grains, tiny particles of silicates and carbon compounds, absorb starlight and re-emit it in the infrared, further aiding the cooling. Over time, these processes bring the gas to a thermal balance with its environment. often stabilizing at around 10 Kelvin. In the densest cores, where even the faint radiation of the cosmic microwave background is absorbed, temperatures can sink slightly lower. These are among the coldest, long-lasting environments in nature, second only to the extraordinary exceptions like the Boomerang Nebula. Cold in the interstellar medium is not static. It is dynamic, shaping the destiny of galaxies. Without cooling, gravity could never gather matter into dense enough clumps to form stars. The gas would remain diffuse, pressure resisting collapse. But when the gas can radiate energy efficiently, its temperature drops, pressure weakens, and gravity gains the upper hand. The collapse begins, and stars are born. In this sense, cold is the midwife of creation. Every star in the sky, including the sun, began as a cold reservoir in a molecular cloud, where temperatures had fallen so low that matter could no longer resist its own weight. For astronomers, probing these regions requires ingenuity. Visible light cannot penetrate them, for the dust absorbs and scatters photons too effectively. Instead, researchers turn to radio, millimeter, and submillimeter wavelengths. Facilities such as the Atacama Large Millimeter Array in Chile or the IRAM telescopes in Spain and France provide the sensitivity and resolution needed to map the hidden structure of these cold clouds. Observations reveal not only the presence of carbon monoxide and ammonia, but also complex organic molecules, some of which are precursors to life's chemistry. The fact that these molecules survive and even thrive at temperatures near 10 Kelvin is testimony to the preserving power of cold, which locks structures in place and prevents chemical reactions from destroying them. These reservoirs remind us that cold is not merely a limit, but also a condition of possibility. It is the environment in which stars gestate, the womb of the galaxy. The temperatures here are beyond anything Earth produces naturally, lower even than the chill of Pluto or Triton. And yet, they are not lifeless voids. They are nurseries of energy and light, waiting for the spark of gravity to ignite. From their shadows come the luminous beacons that fill our skies. When astronomers look toward the constellation Orion, they see one of the most striking displays of stellar birth in the sky. Bright young stars illuminate sprawling clouds of gas, and against this glowing backdrop, a small protrusion juts forward, casting a silhouette shaped like the head of a horse. This is the Horsehead Nebula, a dense molecular cloud of cold gas and dust located about 1,300 light-years from Earth. Its darkness is not absence but presence, a sign that the cloud is so thick it blocks visible starlight from behind. Infrared and millimeter observations, however, pierce the veil and reveal the cold gas within, measured at roughly 10 Kelvin. This frigid temperature preserves the molecules that make up the cloud and allows gravity to work slowly, gathering matter into denser clumps. The Horsehead is not a static sculpture but an evolving structure, eroded by radiation from nearby hot stars, even as its densest pockets may collapse to form new suns. Barnard 68 is another striking example, though on a much smaller scale. Situated about 500 light-years away in Ophiuchus, this dark nebula appears as a round void against a background of countless stars. To the unaided eye, it resembles a hole punched in the sky, yet in reality it is an opaque ball of gas and dust, about half a light-year across. Astronomers measuring its properties find internal temperatures of about 10 Kelvin, and the density is high enough that no visible light penetrates. Studies suggest that Barnard 68 is on the verge of gravitational collapse. Within a few 100,000 years, perhaps less, its core may ignite the birth of a new star. What looks to us like emptiness is in fact a cold, quiet prelude to creation. Such clouds are not rare exceptions. The Milky Way is threaded with them, long filaments stretching tens of light years, forming a skeleton of cold matter that underlies the luminous spiral arms. Giant molecular clouds, like those in Orion or in the Carina region, contain hundreds of thousands of solar masses of material. They are immense storehouses of cold, shaping the rhythm of star formation across the galaxy. The interplay of turbulence, magnetic fields, and radiation determines which parts collapse and which remain diffuse. But everywhere, the cooling is essential. Without reaching these low temperatures, the gas would never condense enough for stars to ignite. Cold is not a byproduct of star formation, it is its requirement. Observing these environments pushes technology to its limits. Instruments must detect faint millimeter and submillimeter radiation from molecules spread across vast distances. The Atacama Large Millimeter Array, perched high in the Chilean Andes, takes advantage of the thin, dry air at 5,000 meters elevation to reduce interference from Earth's atmosphere. With its 66 high-precision antennas working together as an interferometer, ALMA can resolve structures within distant molecular clouds with extraordinary clarity. Astronomers can trace filaments only a few tenths of a light-year wide, measure velocities of gas down to a fraction of a kilometer per second, and map temperature variations of only a few degrees Kelvin. These capabilities allow us to peer into the coldest places of the interstellar medium, reconstructing their internal dynamics from signals that would otherwise be lost in the noise. The chemistry of these clouds is as fascinating as their temperature. Even at 10 Kelvin, molecules form and persist, shielded from ultraviolet radiation by the dense dust. Complex organics such as formaldehyde, methanol, and even amino acid precursors have been detected. The fact that such fragile molecules can survive in such cold environments demonstrates the preservative power of low temperatures. At warmer conditions, they would quickly react and break apart, but here they endure, frozen in time until some process releases them. Comets and asteroids in our own solar system likely inherited much of their chemistry from such interstellar reservoirs. In this way, the cold of molecular clouds connects directly to the origins of planetary systems and perhaps to the emergence of life. The coldness of these clouds also sets them apart from nearly everything else in the universe. Stars blaze at millions of degrees. Supernova remnants glow at tens of thousands. Even the surfaces of icy moons sit hundreds of degrees warmer. Yet here, in the quiet shadows, matter rests only a few degrees above absolute zero. These are places of waiting, of stillness, where time seems to stretch, and yet they are also places of destiny, for without them, galaxies would be sterile collections of aging stars. The balance of cold and gravity ensures that the cycle of birth continues, generation after generation, across billions of years. The existence of cold reservoirs in the interstellar medium reshapes our understanding of galaxies. These clouds are not scattered randomly, but often align along spiral arms, compressed by density waves that sweep through the galactic disk. As the waves pass, gas piles up, cools, and forms molecular complexes. Within them, stars are born, and those stars in turn inject energy back into the medium through radiation, stellar winds, and supernova explosions. The cycle continues endlessly. Cold clouds condense into stars, stars heat and disperse the gas, and new cold clouds eventually form again. In this rhythm, cold is as vital as heat, for without the ability to shed energy, gravity could never overcome pressure. The galaxies would remain diffuse, never lighting their billions of stars. The Milky Way provides ample examples. In the Orion Molecular Cloud Complex, stretching across hundreds of light years, observations reveal a mixture of newborn stars, glowing nebulae, and dense, cold filaments. Infrared images from the Spitzer Space Telescope show young stellar objects embedded within cocoons of dust, their warmth barely breaking through the surrounding chill. Meanwhile, in regions like the Carina Nebula, massive stars have already ignited, their radiation carving cavities in the cold gas around them. These contrasting pictures reveal the delicate interplay of creation and destruction, all driven by the tension between heat and cold. From a chemical perspective, these cold reservoirs are archives of cosmic history. Dust grains within them carry ices of water, carbon monoxide, ammonia, and methane, layered over millions of years. When stars eventually ignite, their heat liberates these ices, seeding the surrounding space with molecules. Comets in young planetary systems preserve these signatures, and in the case of our own solar system, they may have delivered water and organic compounds to Earth. Thus, the cold of interstellar clouds is not only a condition for star formation, but also a preserver of chemistry, holding the building blocks of life in deep freeze until the right conditions arise. In this sense, cold is a guardian of potential, conserving fragile molecules across cosmic time. Technological advances continue to refine our view. Beyond ALMA, future instruments such as the James Webb Space Telescope probe these cold regions in infrared, revealing stars in their earliest moments, still wrapped in dense envelopes. Space missions like Herschel, which operated from 2009 to 2013, mapped the far infrared glow of dust across the galaxy, showing vast webs of cold filaments threaded like nerves through the interstellar medium. These observations emphasize that the coldest regions are not rare curiosities, but central features of galactic ecology. They are the scaffolding upon which star systems like our own take shape. Yet, even as molecular clouds represent some of the coldest persistent environments in nature, they do not claim the ultimate title. Their temperatures hover near 10 Kelvin, perhaps a little lower in shielded cores. That is far above the 2.7 Kelvin background of the cosmos, and certainly above the extraordinary 1 Kelvin of the Boomerang Nebula. Still, these clouds prepare the stage. They teach us that cold is essential for creation, that it is not merely absence but presence, a necessary state, without which stars and planets would never exist. They also teach us that the cosmos is not uniform but a patchwork of extremes, blazing cores, glowing nebulae, and silent, frozen reservoirs. As we close this chapter, we stand ready to turn to something more unusual. The molecular clouds are cold by necessity, their physics dictated by the balance of radiation and collapse. But the coldest known place in the universe emerges from a more dramatic story. It is not a quiet nursery, but a violent transition, a star at the end of its life, ejecting its outer layers into space. In that furious outpouring of gas lies a paradox, the creation of the coldest natural temperatures ever measured. To understand it, we must journey from the calm shadows of molecular clouds to the violent winds of a dying star. There, in a nebula shaped like an hourglass, we will encounter the very edge of natural cold. In 1995, astronomers using the Swedish ESO submillimeter telescope in Chile detected something extraordinary in the constellation Centaurus. While surveying objects known as protoplanetary or pre-planetary nebulae, they stumbled upon a cloud of gas and dust whose properties defied expectations. Among dozens of such objects studied, this one stood out. It appeared unusually bright in submillimeter wavelengths, indicating that it was radiating far more strongly at these energies than its peers. When researchers calculated its temperature, the result was astonishing. The nebula measured at about 1 Kelvin, colder than the cosmic microwave background itself. In other words, here was a natural object, created by a dying star, that was chillier than the universal floor of 2.7 Kelvin. This discovery would soon be recognized as the Boomerang Nebula, the coldest known place in the natural universe. The name came from its shape, glimpsed in optical observations as a lopsided, faint reflection nebula, resembling a boomerang. Later imaging revealed a more symmetric hourglass structure, with lobes extending outward from a central star. The apparent asymmetry had been a trick of limited resolution. In reality, the Boomerang Nebula was a pre-planetary nebula, a brief stage in stellar evolution lasting only a few thousand years. At its center was a red giant star in the process of shedding its outer layers, ejecting vast amounts of gas into space at speeds of hundreds of thousands of kilometers per hour. That ejected material formed an expanding cocoon, which cooled rapidly as it spread. The result was a temperature lower than any other measured in the cosmos. The initial discovery was followed by further study. Astronomers were skeptical at first, for the idea of an object colder than the cosmic background seemed almost paradoxical. Yet repeated observations confirmed the result. The key was that the gas was expanding so quickly that it cooled adiabatically, faster than background radiation could reheat it. Just as a refrigerator lowers the temperature of its contents by forcing gas to expand within coils, so too did the Boomerang Nebula create a natural, cosmic-scale refrigerator. But unlike human machines, it required no power source other than the dying throes of a star. This was nature's own cryogenic experiment, playing out on a canvas 1 light-year wide. The Atacama Large Millimeter Array, later provided detailed images of the nebula, resolving its hourglass structure with unprecedented clarity. ALMA revealed that the cold gas extended for nearly a light year, shaped into twin lobes by the geometry of the outflow. It also showed intricate knots and clumps, evidence of turbulence and asymmetries in the mass loss from the central star. The high-resolution data confirmed the astonishingly low temperature, about 1 Kelvin, across much of the nebula. Such a value is not merely colder than Pluto or Triton, not merely colder than molecular clouds, but colder than the very radiation that fills the universe. The Boomerang Nebula is unique in this respect, the only natural object we know of that defies the universal baseline. The discovery of the Boomerang Nebula changed the way astronomers thought about extreme environments. Until then, the coldest known places were the dense cores of molecular clouds, which reached about 10 Kelvin. The idea that a stellar outflow could cool to 1 Kelvin was unprecedented. It highlighted the importance of rapid expansion as a cooling mechanism, one that can briefly outpace the reheating effect of the cosmic background. The boomerang is thus a fleeting stage, a temporary phenomenon. In time, as the central star evolves into a white dwarf and the gas slows and disperses, the temperature will rise again. But for now, and for the next several thousand years, the nebula holds its record as the coldest natural place in the universe. From our vantage point, the Boomerang Nebula appears faint, requiring powerful telescopes to study. It lies about 5,000 light-years away, far beyond the reach of human exploration. Yet through radio and submillimeter astronomy, we can probe its depths and reconstruct its history. In doing so, we glimpse not only the physics of a dying star, but also the limits of temperature in nature. Here, in this fragile hourglass, lies a cosmic paradox. The end of stellar life, producing not heat and fire, but cold beyond imagination. The claim that the Boomerang Nebula was colder than the cosmic microwave background demanded careful scrutiny. In astronomy, extraordinary results require extraordinary evidence, and this was no exception. When researchers first analyzed the submillimeter radiation detected from the nebula, they realized that its intensity was inconsistent with an object in equilibrium with the background. Normally, any interstellar gas cloud would settle near 2.7 Kelvin, since the bath of photons from the early universe constantly warms matter to that temperature. Yet here, the emission indicated a temperature near 1 Kelvin. To confirm such an unusual value, astronomers needed to test the result with multiple methods and instruments, checking again and again to ensure that what they saw was real. The first line of confirmation came from the physics of molecular absorption and emission. In cold gas, molecules, such as carbon monoxide, occupy only their lowest energy states. Transitions between these states emit radiation at specific frequencies, and the relative strength of these lines reveals the temperature of the gas. In the Boomerang Nebula, the lines were consistent with excitation temperatures around 1 Kelvin. This matched the earlier broadband measurements and provided an independent check. Later observations with ALMA reinforced this picture, showing that the gas indeed maintained such astonishingly low conditions across large volumes. The consistency of results across different instruments and techniques silenced initial doubts and established the boomerang as unique. The structure of the nebula itself helps explain why this is possible. The central star is expelling material at extraordinary speeds, around 500,000 kilometers per hour, far faster than the typical outflows of aging red giants. This rapid expansion is the key. In physics, when a gas expands without exchanging heat with its surroundings, its temperature drops, a process called adiabatic cooling. On Earth, the principle is used in refrigerators and air conditioners, where compressed gas expands and becomes cold. In the Boomerang Nebula, the same principle operates on cosmic scales. The gas expands so quickly that it outruns the warming influence of background photons. Before radiation can restore equilibrium, the temperature plunges to levels lower than the CMB itself. Imaging from ALMA revealed details of the hourglass shape that also contribute to the nebula's extreme conditions. The gas is not escaping uniformly, but is funneled into two opposing lobes, leaving a central waist. This geometry likely results from interactions between stellar winds and a possible binary companion, shaping the outflow into its distinctive form. Within the lobes, the density is low enough that collisions between molecules are rare, further limiting opportunities for the gas to reheat. In effect, the nebula acts like a rapidly expanding, insulated chamber, one where energy loss dominates and external heating cannot keep pace. The result is an enormous cryogenic laboratory in the sky. What makes the Boomerang Nebula especially remarkable is its scale. Laboratory experiments on Earth can reach temperatures lower than 1 Kelvin, but only for tiny samples of atoms or molecules, confined within magnetic traps or vacuum chambers. The Boomerang, by contrast, contains mass equivalent to a fraction of the Sun, spread over nearly a light year. To imagine such a vast volume of space at 1 Kelvin is to confront the immensity of natural extremes. Here, temperature is not merely a property of a laboratory sample, but of an entire nebula visible across thousands of light years. The nebula's appearance in visible light differs strikingly from its submillimeter image. To optical telescopes, it is faint, illuminated only by starlight, scattered off surrounding dust. Its boomerang shape was first identified in this way, hence the name. But the true story is hidden at longer wavelengths, invisible to the human eye. Only with specialized detectors can astronomers probe the cold gas directly, mapping its temperature and dynamics. The union of optical, infrared, and radio observations paints a complete picture. A dying star, an expanding envelope, a cosmic refrigerator, sculpted into an hourglass form. The fact that such an environment exists challenges our intuition about stellar death. We might expect that as stars shed their outer layers, they would become brighter and hotter, at least locally. Indeed, many planetary nebulae glow with vivid colors, energized by radiation from their central white dwarfs. The Boomerang Nebula, however, represents an earlier stage, before the core has heated enough to ionize the surrounding gas. Instead of brilliance, it offers shadow. Instead of warmth, it offers cold. This stage is short-lived, lasting only a few thousand years, a fleeting moment in stellar timescales. Yet during this interval, nature produces the coldest known conditions in the cosmos. For astronomers, the Boomerang is a reminder that the universe always has surprises. Just when we think the cosmic microwave background sets an inviolable floor, we find a nebula that slips beneath it. Just when we expect stellar death to blaze with heat, we encounter one that freezes the universe around it. The Boomerang Nebula is therefore not only a record holder, but also a window into processes that challenge our assumptions, expanding the boundaries of what is possible in nature. The uniqueness of the Boomerang Nebula becomes clearer when we compare it with other objects in the same stage of stellar evolution. Many dying stars enter the pre-planetary nebula phase, ejecting shells of gas as they transition from red giants to planetary nebulae. Yet none of those observed so far exhibit temperatures anywhere near 1 Kelvin. They expand, yes, and they cool, but not with the speed or efficiency of the Boomerang. Something about this particular star, perhaps its mass loss rate, or the geometry of its outflow, has conspired to produce the most efficient, natural refrigerator in the universe. The nebula is a reminder that even among stars of similar class, outcomes can diverge dramatically, yielding singular phenomena that stand apart from all others. Its temporary nature adds to its significance. The conditions that keep the Boomerang colder than the cosmic microwave background will not last forever. As the gas continues to expand, its density will drop, and eventually radiation from the central star, as it contracts toward a white dwarf, will begin to heat the surrounding material. The nebula will brighten, becoming more like the colorful planetary nebulae familiar in astronomical catalogs. The extraordinary cold will vanish, replaced by glowing shells, energized by ultraviolet light. In cosmic terms, this change is imminent, likely within just a few thousand years. For now, though, we are fortunate to observe the nebula in this rare and fleeting stage, a brief window into an extreme that the universe seldom allows. The Boomerang Nebula's discovery also emphasizes the importance of multi-wavelength astronomy. In visible light, it appears faint and ghostly, difficult to study in detail. Only through submillimeter and millimeter observations could astronomers measure its temperature and map its structure. Instruments such as ALMA, with their unparalleled resolution and sensitivity, are what make it possible to confirm the existence of a 1 Kelvin nebula, thousands of light years away. This demonstrates the necessity of looking beyond what the human eye can see. The cosmos reveals its most extraordinary secrets only when we widen our senses to embrace the full spectrum of radiation. From a broader perspective, the Boomerang Nebula stands as a natural parallel to the achievements of laboratory physics. On Earth, researchers use laser cooling, magnetic traps, and evaporative techniques to chill atoms to billionths of a Kelvin. These temperatures are lower than what the Boomerang provides, but only in tiny, carefully controlled samples. The nebula, by contrast, spans nearly a light year, holding a vast quantity of gas at a uniform temperature lower than the universal background. It is the scale that astonishes. Where laboratories produce small islands of cold in the sea of a warm world, the Boomerang offers a cosmic continent of cold in the sea of a warm universe. The existence of such a nebula also sharpens our sense of cosmic destiny. It shows that under the right conditions, nature can outpace the universal thermostat of the cosmic microwave background, albeit temporarily. If such extremes are possible in isolated cases today, what of the far future, when the universe itself cools toward absolute zero over trillions of years? The Boomerang may be a fleeting echo of that future, a preview of conditions that will one day encompass all space. In this way, the nebula links the short scale of stellar death with the long arc of cosmic evolution, bridging moments that range from a few thousand years to countless trillions. For now, the Boomerang Nebula remains a singular marvel, a place that pushes natural conditions to their limits. It is both fragile and immense, fleeting and timeless. A star, in its dying gasp, has created not fire but frost, not light but shadow, not heat but the deepest cold known to science. As we leave this nebula behind, the next step is to understand why such extremes occur, to delve into the physics of expansion, cooling, and energy balance. The Boomerang is not just a curiosity, it is a classroom, teaching us lessons about the fundamental principles of thermodynamics on the grandest of scales. To continue, we must turn from observation to explanation, from the telescope to the theory, and examine the physics behind the extreme cold. The Boomerang Nebula confronts us with a paradox. How can a dying star, an object normally associated with the release of heat and radiation, create a region of space colder than the background of the universe itself? To answer this, we must step into the realm of thermodynamics, the science of energy and its transformations. The nebula is not a mystery outside known physics, but rather a dramatic illustration of principles we use in everyday machines. Its coldness arises from expansion, from the way gases behave when they spread rapidly into lower pressure, and from the balance between energy loss and energy input. What happens inside the Boomerang Nebula is a cosmic-scale version of what happens every time a refrigerator cools its contents. In thermodynamics, temperature is tied directly to the average energy of microscopic motion. When molecules collide and vibrate with great vigor, the temperature is high. When their motions slow, the temperature falls. Energy can leave a system in different ways, through conduction, convection, or radiation. But there is another mechanism, one tied to the volume of the system. If a gas expands without receiving heat from outside, the energy that once went into random motion must now be shared across a greater volume. As a result, the particles move more slowly on average, and the temperature drops. This is adiabatic expansion, and it is the heart of the Boomerang Nebula's story. On Earth, we harness this principle in refrigerators and air conditioners. A working fluid, often a compressed gas, is allowed to expand rapidly through coils or valves. As it expands, it cools, absorbing heat from its surroundings. That heat is then expelled elsewhere as the cycle repeats. The process requires energy input, usually electricity, to keep the cycle going, but the principle of expansion, leading to cooling, is the same. In the Boomerang Nebula, The star itself provides the energy, not in the form of electricity, but in the kinetic blast of stellar winds. The gas thrown off by the dying star races outward at speeds of about 500,000 kilometers per hour, expanding into space so quickly that it undergoes adiabatic cooling on a colossal scale. The rate of this expansion is crucial. Normally, interstellar gas exchanges heat with its surroundings, absorbing photons from starlight or from the cosmic microwave background. Over time, such gas settles into equilibrium near 2.7 Kelvin, the universal baseline. But if the gas expands faster than it can absorb energy, its temperature plummets below that baseline. In the Boomerang Nebula, the velocity of the outflow is unusually high, and the density of the gas is such that interactions with background photons are too infrequent to keep pace. The result is a region colder than the cosmic background, not because the laws of physics are broken, but because the process is faster than the environment can respond. Another way to understand this is to imagine standing near a compressed can of air. When the nozzle is opened, the gas rushing out feels cold against the skin. Energy is not disappearing, but it is being redistributed. Pressure energy converts into kinetic energy of expansion, leaving less energy available for the random thermal motions of molecules. In the Boomerang Nebula, this effect is magnified across billions of trillions of molecules, with the entire envelope of a star undergoing the same rapid transformation. Instead of warmth, the result is chill, a super refrigerator powered by stellar death. The geometry of the nebula contributes to its ability to maintain such conditions. The outflow is not uniform, but shaped into twin lobes, with material funneled through a narrow waist. This configuration may be caused by the presence of a binary companion or by magnetic fields guiding the flow. Whatever the origin, the hourglass shape ensures that the gas expands efficiently into space, maximizing the cooling effect. The low density of the lobes also means that collisions between molecules are rare, further reducing the chances of reheating. In combination, these factors create a perfect storm for natural refrigeration, one capable of beating the cosmic microwave background at its own game. Understanding the physics behind the Boomerang Nebula illuminates the elegance of natural law. The same equations that describe the cooling of compressed air or the efficiency of engines apply here, across a gulf of thousands of light years. There is no hidden force or unknown energy at work. Instead, the nebula is an example of the universe exploiting the principles of thermodynamics in dramatic fashion. It is a reminder that the cosmos, for all its vastness, obeys the same rules we observe in the laboratory, and that sometimes those rules combine in ways that surprise us. The comparison between the Boomerang Nebula and a household refrigerator may seem strange at first, yet it is more than metaphor. Both rely on the same physical principle: expansion cools. In a refrigerator, the process is tightly engineered. A compressor squeezes the refrigerant into a high-pressure liquid. That liquid then passes through an expansion valve into a region of lower pressure, where it rapidly vaporizes. The expansion absorbs heat, lowering the temperature of the surrounding compartment. The cycle repeats, powered by electricity, to maintain an environment just a few degrees above freezing. In the Boomerang Nebula, there is no compressor, no valves, and no wires. Yet the same principle operates on a far grander scale. The star's dying breath acts as the compressor. Its gravity and nuclear changes, forcing gas outward at extreme velocities. As that gas expands into the emptiness of space, it cools faster than background radiation can restore balance. The effect is not localized to a kitchen appliance, but spread across a volume nearly a light year wide. To maintain such conditions requires not only rapid expansion, but also a delicate interplay of density and radiation. If the gas were denser, collisions between molecules would redistribute energy more effectively, raising the temperature. If it were thinner, radiation from the cosmic microwave background would penetrate more easily, again preventing the temperature from dropping so far. The Boomerang Nebula occupies a unique middle ground. Its density is low enough to minimize collisions, but high enough to shield against background photons. This balance creates an environment where adiabatic cooling dominates, driving temperatures below the universal baseline. The nebula is a natural fine-tuning, an accidental alignment of parameters that makes it the coldest known place in the universe. The transience of this state cannot be overstated. The Boomerang Nebula is in a stage of evolution that lasts only a few thousand years, a blink of an eye in cosmic terms. Already, the gas is moving outward, spreading thinner with each passing century. Eventually, the star at its center will contract into a white dwarf, becoming hot enough to emit ultraviolet radiation. That radiation will ionize the surrounding gas, transforming the Boomerang into a typical planetary nebula, glowing with the colors of oxygen, nitrogen, and hydrogen. When that happens, the frigid temperatures will vanish, replaced by shells heated to thousands of degrees. What we see now is temporary, a cosmic photograph of a rare moment, captured by chance during the brief interval when the nebula acts as a natural cryogenic chamber. On Earth, physicists have achieved even lower temperatures, though only in tiny amounts of matter. Through techniques such as laser cooling, magnetic trapping, and evaporative cooling, researchers can bring clouds of atoms to billionths of a Kelvin above absolute zero. In 1995, these methods produced the first Bose-Einstein condensates, where atoms collapse into a single quantum state, behaving like one giant atom. Such laboratory achievements push beyond the Boomerang in terms of raw temperature, but the comparison highlights the distinction between scale and absolute value. Laboratories achieve their results in samples of thousands or millions of atoms. The Boomerang Nebula sustains 1 Kelvin across a mass comparable to the Sun, spread over nearly a light year. The difference is staggering. Human technology surpasses nature in depth, but not in breadth. This contrast illustrates a broader truth about physics. Nature provides the principles, and humans learn to manipulate them. The Boomerang Nebula cools through adiabatic expansion, without intention or design, simply following the path set by its conditions. On Earth, engineers mimic that principle deliberately, building machines that exploit expansion to provide refrigeration and air conditioning. In laboratories, physicists refine it further, using lasers to manipulate individual atoms, reaching temperatures nature rarely attains. Both realms demonstrate the universality of thermodynamics. Whether in a kitchen, in a cryogenic laboratory, or in a dying star, the same laws apply. The Boomerang Nebula's fleeting cold also carries a lesson about the impermanence of extremes. The universe allows such conditions only briefly, in special circumstances, before processes restore balance. Cold is never permanent, because energy is never absent. Even at 1 Kelvin, the molecules in the nebula vibrate faintly, their motions limited by the uncertainty principle of quantum mechanics. Absolute zero remains unattainable, both in the laboratory and in space. The Boomerang has come closer than any natural object known, but it too will rise, warmed by the evolution of its star and the diffusion of its gas. Its title as the coldest natural place in the universe is secure for now, but not forever. The story of the Boomerang Nebula also sharpens the contrast between natural and artificial extremes. On Earth, researchers have coaxed atoms to temperatures unimaginably close to absolute zero, lower than 1 billionth of a Kelvin. These values eclipse anything found in space, even the Boomerang itself, but they exist only within the confines of laboratories, carefully shielded from disturbances and sustained by constant input of energy and control. The universe, left to its own devices, rarely achieves such precision. Instead, its coldest places arise, not from design, but from circumstance, from the interplay of expansion, shielding, and radiation. The Boomerang Nebula demonstrates that natural processes can, on rare occasions, rival the feats of human engineering, but it also reminds us that scale matters. A laboratory trap contains a speck of ultra-cold atoms. The nebula contains nearly a solar mass of gas, all sustained near 1 Kelvin. In this balance of depth and scale, both nature and humanity reveal their ingenuity. The physics behind these extremes is not esoteric but fundamental. Adiabatic cooling, the redistribution of energy in expansion, underpins both refrigerators and nebulae. Radiation exchange, The constant interplay between matter and the cosmic microwave background defines the baseline for temperature in the cosmos. Quantum mechanics, through the uncertainty principle, ensures that absolute zero can never be reached, no matter how far we push. Each of these principles converges in the Boomerang Nebula, creating a cosmic classroom where the laws of thermodynamics unfold on a grand canvas. By studying this nebula, astronomers not only map a distant object, but also confirm the universality of physics across unimaginable scales. In reflecting on the boomerang, we see that cold is not simply the absence of heat. It is a dynamic state, a balance between energy loss and energy gain, a measure of how matter interacts with its environment. In molecular clouds, cold allows stars to form. In comets, cold preserves the chemistry of the early solar system. In laboratories, cold reveals quantum behaviors, otherwise hidden. In the Boomerang Nebula, cold emerges as a fleeting miracle, a consequence of stellar death producing not fire but frost. Across all these settings, the thread is the same. Temperature governs destiny, shaping the form and fate of matter. The temporary nature of the boomerang's coldness also underscores the transience of extremes in the universe. Stars are born, shine, and die. Gas clouds collapse, ignite, and disperse. Even galaxies merge and evolve. The coldest places, like the hottest ones, are stages in a cosmic drama that unfolds over billions of years. To catch the Boomerang Nebula in this moment is to glimpse a rare act, one that will not repeat in quite the same way. For future astronomers, perhaps tens of thousands of years from now, the nebula will no longer be the coldest place. It will be an ordinary planetary nebula, glowing faintly as its central white dwarf cools. But the record of its past will remain, written in the data we gather today. This understanding leads naturally into broader questions. If a single dying star can create such extremes, what does this tell us about the universe's ultimate trajectory? Can the cosmos itself, expanding ever outward, mirror the adiabatic cooling of the boomerang? Will the universe one day become as cold as this nebula, stretched so thin that all energy is diluted into silence? These questions push us toward the future chapters of our story, where the fate of cosmic temperature itself comes into focus. For now, the Boomerang Nebula stands as a singular reminder that even in the act of ending, stars can create new beginnings, new lessons, and glimpses of what lies ahead. It is not just a curiosity tucked away in Centaurus, but a clue to the deepest workings of the cosmos. While the Boomerang Nebula holds the record for the coldest known natural environment, humanity has learned how to press the boundary of temperature even further, though on vastly smaller scales. The quest to cool matter to its lowest possible states is not driven by curiosity alone, but by the desire to probe the fundamental laws of physics. Cold is not only absence of heat, but also a magnifying glass, a condition in which quantum behavior, once hidden by thermal agitation, emerges into the open. In laboratories across the world, scientists have pushed atoms and molecules to temperatures far lower than 1 Kelvin, achieving feats nature rarely attempts. These accomplishments represent one of the great triumphs of modern physics, revealing worlds invisible to ordinary conditions. The story begins with the liquefaction of gases. In the 19th century, researchers worked tirelessly to lower the boiling points of substances by compressing and cooling them. Oxygen, nitrogen, and hydrogen were liquefied, providing the first steps into cryogenics. The breakthrough came in 1911, when Dutch physicist Heike Kamerlingh-Onnes succeeded in liquefying helium, reaching temperatures only a few degrees above absolute zero. In doing so, he discovered superconductivity, a phenomenon where electrical resistance vanishes in metals cooled below a critical threshold. This was the first demonstration that new states of matter reveal themselves only at extremely low temperatures. Onnes had opened a door that would never again close, and generations of scientists followed him through. In the decades that followed, methods of cooling grew increasingly refined. By pumping liquid helium and allowing it to evaporate under reduced pressure, physicists could reach fractions of a Kelvin. Superfluid helium, discovered in the 1930s, flowed without viscosity, climbing the walls of its container in defiance of intuition. These discoveries showed that matter at low temperatures behaves in ways that classical physics could not predict. To understand them required the language of quantum mechanics, and each experimental milestone deepened the bond between theory and observation. Cryogenics became not just a technical pursuit, but a frontier where the deepest principles of nature were revealed. By the late 20th century, researchers were no longer satisfied with fractions of a Kelvin. They aimed to approach absolute zero itself, not in bulk matter, but in individual atoms. The advent of laser cooling in the 1970s and 1980s made this possible. By tuning lasers to just below the resonance frequency of an atom, photons could be used to slow its motion, each absorption and emission nudging it toward rest. Magnetic and optical traps held the atoms in place as they lost momentum, their temperature dropping to millionths, then billionths of a Kelvin. In 1995, this technique culminated in the creation of Bose-Einstein condensates, a new state of matter predicted decades earlier by Satyendra Nath Bose and Albert Einstein. In this state, atoms collapsed into a single quantum wave, indistinguishable from one another, behaving as one entity spread across space. For this achievement, Eric Cornell, Carl Wieman, and Wolfgang Ketterle received the Nobel Prize in Physics. The temperatures reached in these experiments are astonishing. Whereas the Boomerang Nebula hovers near 1 Kelvin, laboratories on Earth have cooled atoms to below 1 billionth of a Kelvin. This is colder than any natural environment known in the cosmos. Yet the comparison highlights a paradox. On one hand, human ingenuity surpasses nature in absolute terms, creating conditions the universe itself does not. On the other hand, the scale is minuscule. A cloud of ultra-cold atoms contains perhaps 1 million or 1 billion particles, suspended in a vacuum chamber the size of a coin. The Boomerang Nebula, by contrast, holds mass equivalent to the Sun, stretched over nearly a light year, all chilled to 1 Kelvin by natural forces. The contrast between scale and depth illustrates the complementary roles of human and cosmic extremes. The pursuit of laboratory cold is not a curiosity for its own sake. It has transformed physics. At ultra-low temperatures, superconductivity and superfluidity are magnified. Bose-Einstein condensates reveal collective quantum states, and precision measurements become possible that test the foundations of physical law. Cold slows time for atoms, allowing clocks based on their oscillations to achieve unprecedented accuracy. Cold suppresses thermal noise, enabling detectors to register signals otherwise drowned out. Cold reveals the quantum structure of matter, hinting at new technologies yet to come. What the Boomerang Nebula demonstrates on a cosmic stage, laboratories demonstrate on a microscopic one. That temperature governs what matter can be, and by pushing it lower, we unlock new realms of behavior. The creation of Bose-Einstein condensates in 1995 was more than just a technical milestone. It was the unveiling of a new state of matter, one that had lived in the realm of theory for nearly 70 years. Einstein, building on the work of Indian physicist Satyendra Nath Bose, had predicted that if a collection of boson's particles that follow specific statistical rules were cooled to sufficiently low temperatures, they would all collapse into the same lowest energy state. Instead of behaving as many particles, they would behave as one, a single wave spread across space. This prediction lingered on the edge of possibility for decades, awaiting a way to cool atoms to the necessary regime. With the invention of laser cooling and magnetic trapping, it finally became reality. When Cornell and Wieman produced the first condensate using rubidium atoms, and Ketterle soon followed with sodium, the quantum world spilled outward into the macroscopic. A new era of physics had begun. In the laboratory, the methods used to achieve such cold seem almost like magic. Lasers, usually thought of as sources of heat, can in fact cool atoms when tuned just right. By adjusting the frequency slightly below the natural resonance of the atom, photons are absorbed preferentially when atoms move toward the laser, slowing them with each interaction. Repeated from multiple directions, This technique creates what physicists call optical molasses, a viscous environment where atoms are slowed to near stillness. Magnetic traps then confine them, preventing escape, while evaporative cooling removes the most energetic atoms, leaving behind an even colder sample. With patience and precision, the temperature drops to millionths and then billionths of a Kelvin, a realm where quantum mechanics no longer hides in the background, but dominates every aspect of behavior. These techniques reveal striking parallels with the natural world. Just as the Boomerang Nebula achieves extreme cold through expansion, laboratory methods achieve it through careful control of energy distribution. Both rely on the same thermodynamic principles, though on vastly different scales. The nebula produces 1 Kelvin across a light year through the violent expulsion of gas. A laboratory produces 1 billionth of a Kelvin in a vacuum chamber through the delicate nudge of photons. Each, in its own way, pushes matter towards stillness, stripping away thermal motion until only the fundamental rules remain visible. The discoveries made at these temperatures have reshaped modern science. Bose-Einstein condensates allow the study of superfluidity in unprecedented detail, with atoms flowing without resistance through traps and channels. Vortices, quantum whirlpools, form in the condensates, behaving like miniature models of cosmic structures. Precision measurements of atomic interactions test the limits of quantum theory. Ultracold atoms trapped in optical lattices simulate the behavior of electrons in solids, giving researchers insight into materials that might one day revolutionize technology. In every case, the ability to cool matter to extreme levels acts as a key, unlocking doors to phenomena hidden at ordinary temperatures. One of the most striking comparisons lies in the timescales involved. The Boomerang Nebula's coldness will persist for only a few thousand years before reheating. Laboratory condensates last only seconds before disturbances destroy them. Both are temporary, fragile states, sustained by special conditions and destined to vanish. Yet during their brief existence, they reveal profound truths. The nebula shows us that nature itself can surpass the cosmic microwave background. The condensates show us that human ingenuity can surpass nature. Together, they demonstrate that temperature is not just a measure of heat, but a gateway to understanding the very fabric of reality. For all their differences, these extremes converge on a single lesson. Cold is a tool. In the cosmos, it allows stars to form, preserves chemistry, and reveals fleeting marvels like the Boomerang Nebula. In the laboratory, it allows scientists to probe quantum mechanics, build precision technologies, and explore states of matter never before seen. Both remind us that the universe is richer and stranger when we move closer to absolute zero. Far from being mere absence, cold is creation of order, of discovery, of insight. In considering laboratory cold against the backdrop of cosmic extremes, one theme stands out: scale. The Boomerang Nebula holds a mass comparable to the Sun and stretches nearly a light year across, yet achieves only 1 Kelvin. Human experiments reach temperatures a billion times colder, but in clouds of atoms too small to see without microscopes. Nature gives us breadth. Humanity achieves depth. Both are achievements in their own right, and both highlight different aspects of what it means to approach absolute zero. Neither diminishes the other. Instead, they reveal the complementary ways in which the universe and human ingenuity explore the boundaries of possibility. The pursuit of laboratory cold also reshapes how we think about the fundamental laws of physics. At room temperature, the quantum world is hidden beneath a wash of thermal motion. Electrons, atoms, and molecules behave chaotically, their quantum states colliding and decohering before we can measure them. But at ultra-low temperatures, the noise quiets. Quantum mechanics, usually confined to the scale of the microscopic, spills into the macroscopic. In Bose-Einstein condensates, entire clouds of atoms act as one wave function. In superconductors, electrons pair up and flow without resistance. In superfluids, helium defies viscosity, climbing walls and forming frictionless films. These are not exotic violations of physical law, but natural consequences of lowering temperature. Cold unveils what has always been there, hidden by heat. The philosophical implications are profound. When we look at the Boomerang Nebula, we see a natural process revealing the laws of thermodynamics on a cosmic scale. When we build ultra-cold laboratories, we see human minds bending those same laws to reveal quantum mechanics in its purest form. Both efforts underscore a truth. The universe is governed by principles that are universal and repeatable. Expansion cools whether in a refrigerator or a dying star. Quantum condensation emerges whether in rubidium atoms in Colorado or sodium atoms in Massachusetts. These connections remind us that science is not about isolated curiosities, but about the deep unity of physical law across every scale of existence. The impermanence of cold, whether natural or artificial, also deserves reflection. The Boomerang Nebula will eventually reheat, its fleeting record lost to time. Bose-Einstein condensates evaporate within seconds, vanishing as quickly as they form. Absolute zero remains forever out of reach, guaranteed by the third law of thermodynamics. Yet in this impermanence lies meaning. Extremes are valuable, not because they last forever, but because they reveal what lies beneath. Just as lightning illuminates the night sky for an instant, cold illuminates the laws of matter in brief windows of clarity. The moment may pass, but the knowledge remains. When we place human achievements next to cosmic extremes, a continuity emerges. Cold is a spectrum, stretching from Antarctica's -90 degrees Celsius, through Pluto's -225, down to the Boomerang Nebula's 1 Kelvin, and finally into the billionths of a Kelvin produced in laboratories. At every step, new phenomena appear. Weather and climate give way to frozen worlds. Frozen worlds give way to molecular clouds. Molecular clouds give way to nebulae colder than the cosmic microwave background. Laboratories push beyond even that, into a realm where matter behaves collectively as a quantum whole. The journey is continuous, a descent toward absolute zero that reveals new wonders at each level. As Chapter 7 closes, we are left with a sense of both humility and triumph. Humility, because nature on its own produces phenomena like the Boomerang Nebula that stretch our imagination. Triumph, because human beings, with lasers and magnets, have surpassed nature in sheer proximity to absolute zero. Both perspectives enrich the story. Cold is not simply the absence of heat. It is a stage where the universe's deepest truths emerge, whether in dying stars or in laboratories on Earth. To move forward, we must now step back to a broader view, examining what cold means not just as a record of extremes, but as a force that preserves, shapes, and limits the possibilities of matter itself. Cold is not only an extreme to be measured, it is also a condition that shapes the destiny of matter, preserving some things while preventing others. At its most fundamental level, temperature is motion. When molecules slow, when vibrations diminish, reactions falter. In this sense, cold acts as both guardian and jailer, locking the past into place, even as it restrains the present from unfolding. The universe is filled with examples where cold preserves fragile chemistry across eons, yet also where it stands as a barrier, forbidding activity, halting processes, and keeping matter in suspended stillness. Nowhere is this dual role more evident than in the icy archives of the solar system and the frozen expanses of its moons and comets. Consider the comets that drift in the outer solar system, relics from the birth of planets more than 4.5 billion years ago. These small bodies, composed of rock, dust, and volatile ices, orbit in distant reservoirs, such as the Kuiper Belt and the Oort cloud. Far from the warmth of the sun, they remain locked in deep freeze, their chemistry unchanged for billions of years. Water, ice, carbon dioxide, methane, and ammonia remain trapped within them, preserved as if in a cosmic time capsule. When a comet occasionally falls inward toward the inner solar system, the sun's heat awakens it. Ices sublimate, producing tails of gas and dust that stretch across millions of kilometers. Yet the material released is not newly made. It is ancient, a sample of the conditions that prevailed when planets first formed. Without the cold, this chemistry would long ago have been altered or lost. With the cold, it is preserved across cosmic ages. The same principle holds for planetary moons in the outer solar system. Europa, orbiting Jupiter, is locked in a perpetual chill. Its surface temperature averages around -160 degrees Celsius, a frozen crust of water ice that hides a subsurface ocean. That ice, though forbidding, acts as a shield, preserving the ocean beneath from evaporation and from radiation. Enceladus, a smaller moon of Saturn, maintains an even colder surface, but beneath its ice shell, warmth from tidal forces keeps water liquid. Geysers jet into space, carrying with them particles that suggest organic chemistry. Here, again, cold is both preserver and barrier. It prevents life on the surface, freezing all activity, yet it allows oceans to endure for billions of years below, sustained by the balance between cold crust and warm interior. Even on Earth, we see the preservative power of cold. In permafrost, woolly mammoths remain intact for tens of thousands of years, their flesh and hair preserved by frozen soil. In glaciers, ancient air is trapped in bubbles, providing a record of Earth's atmosphere stretching back hundreds of thousands of years. Cold halts decay, slows chemical reactions, and protects fragile molecules from the relentless march of entropy. Astronomers apply the same principle when they consider icy moons and comets. The chemistry we study there has been placed in storage by nature itself, waiting to be thawed by curiosity or chance. In this way, cold is a cosmic archive, a keeper of memory written not in words but in molecules. But preservation comes at a cost. Where cold slows change, it also prevents growth. In the outer solar system, life struggles not because there are no building blocks, but because the temperatures are too low for reactions to proceed. Metabolism requires energy, and extreme cold suppresses it. The same ice that protects chemistry from decay also prevents it from organizing into complexity. Cold is thus both gift and obstacle. It safeguards the past while delaying the future. It creates time capsules of what was, while limiting the emergence of what could be. This duality defines much of the outer solar system and extends into interstellar space, where cold clouds preserve molecules, but inhibit the reactions that might otherwise lead to life. Cold shapes the solar system as much as heat does. Nowhere is this clearer than in comets, which spend most of their lives in darkness, orbiting in regions so distant that sunlight is little more than a faint glimmer. The Kuiper Belt, extending beyond Neptune, and the even more remote Oort cloud hold trillions of such icy remnants. Their temperatures remain hundreds of degrees below freezing, and in that deep freeze, chemistry has been arrested since the dawn of planetary formation. When comets are nudged inward by gravitational encounters, their surfaces awaken under sunlight, but their interiors remain pristine. Each visit to the inner solar system releases molecules that tell a story billions of years old. By sampling these gases, spacecraft, such as Rosetta, have confirmed the presence of water, carbon monoxide, carbon dioxide, ammonia, and organic molecules. Without the preserving power of cold, these fragile compounds would never have survived intact from the birth of the solar system to the present day. The role of cold as a preserver also extends to planetary rings. Saturn's rings, composed largely of water ice, shine brightly because their particles remain frozen, reflecting sunlight rather than absorbing it. These particles, likely remnants of a shattered moon or captured comet, orbit in temperatures near -180 degrees Celsius. Cold maintains their integrity, preventing the ice from sublimating into space. At the same time, it restricts change. The rings are dynamic in structure but static in composition, a frozen monument circling a giant planet, shaped more by gravity and collisions than by chemistry. On moons such as Europa and Enceladus, cold draws a sharp line between surface and interior. The ice crusts, frozen solid at temperatures far below water's freezing point, appear barren and lifeless. Yet beneath them lie oceans of liquid water, maintained by tidal heating from the gravitational pull of their parent planets. The contrast is stark, a surface too cold for chemistry to advance, shielding an interior where warmth and water create possibilities. In this way, cold both denies and enables. It denies the surface the chance to evolve complex chemistry, yet it enables the ocean to persist over billions of years, safe from evaporation and radiation. Without the ice, there would be no ocean. Without the cold, there would be no preservation. Life, if it exists there, would owe its very possibility to the balance between warmth below and cold above. Even beyond our solar system, the preservative role of cold echoes in the chemistry of interstellar clouds. Complex molecules such as methanol and formaldehyde have been found frozen onto dust grains, shielded within icy mantles at temperatures near 10 Kelvin. These ices endure for millions of years, preserved until the birth of new stars warms them and liberates their contents into surrounding space. In young stellar systems, the chemistry inherited from these cold clouds, seeds, comets, and planets, with the raw materials of life. Thus, the preservation afforded by cold is not limited to individual comets or moons, but is woven into the very cycle of star and planet formation. Cold ensures continuity across cosmic generations, carrying fragile compounds through time and space until conditions allow them to flourish. But as much as cold preserves, it also restrains. Reactions that would otherwise proceed quickly slow to a crawl in cryogenic environments. Molecular bonds remain unbroken, but new ones seldom form. In the Kuiper belt, in comets, in the icy crusts of moons, and in molecular clouds, chemistry is placed on hold. Cold is a pause button on the processes of complexity. It protects what exists but prevents what might arise. For astrobiology, this is both blessing and curse. The building blocks are there, intact, but locked in stasis. To become life, they must wait for warmth. The same ice that guards them against destruction denies them the spark of activity. Thus, cold stands revealed as a paradoxical force. It is the guardian of memory, preserving ancient chemistry, planetary archives, and interstellar molecules. At the same time, it is the barrier to growth, freezing surfaces, halting reactions, and rendering vast regions of the cosmos sterile. This duality defines the outer solar system and the wider galaxy. Cold is both history and prison, both protector and inhibitor. It is not a simple condition, but a force that shapes what survives and what cannot yet begin. Cold defines boundaries across the cosmos, and in doing so, it sketches both preservation and limitation. On one side of the balance, cold safeguards history. Comets retain the chemistry of the early solar system. Icy moons preserve oceans beneath protective shells, and interstellar grains carry frozen molecules for millions of years until stars are born. In these cases, cold functions as an archivist, keeping the fragile past intact so that later epochs can inherit it. The fact that water still flows on Earth today, and that organic compounds exist in comets and asteroids, is in part because cold held them safe through long ages of exposure to vacuum and radiation. Without cold, much of this heritage would have vanished. The present is built on what the cold preserved. On the other side, cold places barriers that no process can easily overcome. In the outer solar system, surfaces lie locked in stillness, chemical reactions slowed to imperceptibility. Europa and Enceladus may shelter oceans, but their frozen crusts prevent easy access, burying any activity beneath kilometers of ice. In interstellar clouds, molecules cling to dust grains, unable to move freely until a newborn star warms them. Cold's shield is also a wall, a reminder that preservation is inseparable from inhibition. The universe does not hand out archives without cost. The same temperature that guards chemistry also restrains its progress, leaving vast stretches of space quiet and inert. This duality is part of a larger truth. Cold is not merely absence, it is agency. It has power over time. In warm places, processes accelerate, molecules collide, combine, and change. In cold places, time stretches. Chemistry waits, suspended in near stillness, until a spark of warmth breaks the pause. Thus, cold can be understood as a sculptor of pace, determining whether events unfold in moments or over millions of years. The existence of preserved organics in comets, unchanged since the solar system's formation, is evidence of this stretched time. The possibility of oceans under icy moons is evidence of this balance between stasis and endurance. Cold slows, but in slowing, it saves. For humanity, this dual role of cold carries practical resonance. Cryogenics on Earth extends the lifespan of cells, tissues, and materials, just as cosmic cryogenics preserves chemistry in space. Astronomers studying distant icy bodies are in effect reading records maintained by cold. Astrobiologists seeking life in frozen worlds must contend with cold as both preserver of oceans and barrier to habitability. Engineers developing spacecraft to explore these environments must plan for cold as a threat to instruments and as a protector of pristine samples. Across disciplines, the lesson is the same. Cold cannot be thought of as a void. It is an active condition, shaping what is possible and what is not. The broader implication stretches into the destiny of the cosmos itself. The same processes that freeze comets and moons may one day freeze the universe. As galaxies drift apart and stars exhaust their fuel, the universe as a whole will cool. The cosmic microwave background, today at 2.7 Kelvin, will fall further as space expands. Cold will extend its dominion, preserving whatever remains, but also halting further activity. In this sense, the icy archives we see in the present are previews of the universe's long future, a time when preservation will dominate and barriers will stand everywhere. Cold, which now guards fragments of history, will one day guard the cosmos entire. To reach that far future, however, we must first understand the structures already shaped by cold in the universe today. Beyond comets and moons, beyond icy rings and preserved atmospheres, lie even larger regions, the cosmic voids. These are expanses of space so vast and so empty that they dwarf any structure we have yet considered. Within them, cold is not a local phenomenon but a cosmic condition set by expansion itself. As we move forward, we will leave the preserved chemistry of the solar system and step into the grand scaffolding of the universe, where cold emptiness stretches for hundreds of millions of light years. If molecular clouds and icy moons are the small-scale theaters of cold, then cosmic voids are its grandest stage. These are the immense, underdense regions of the universe, vast expanses where matter is scarce and galaxies are few. To the human imagination, they are almost incomprehensible. A typical void may span hundreds of millions of light years, dwarfing entire clusters of galaxies. Within them, the density of matter is so low that even the sparse gas of intergalactic space becomes rarer still. In such realms, cold is not local but cosmic. It is not the cold of ice or the cold of molecular shielding, but the cold of emptiness stretched by expansion. Voids are a natural consequence of cosmic structure. After the Big Bang, tiny fluctuations in density grew under gravity. The denser regions accumulated matter, forming filaments, clusters, and galaxies. The less dense regions emptied out, expanding into voids. The result, when mapped by galaxy surveys, is a cosmic web, bright threads of galaxies surrounding immense dark cavities. These cavities are not truly empty. They contain some gas, a few galaxies, and the ever-present cosmic microwave background. But compared to the richness of clusters, they are deserts in the cosmic landscape. Their defining quality is their lack of density, and with that lack comes a distinct relationship to temperature. Because voids contain little matter, they are dominated by expansion. As space itself stretches, any gas within them thins further, cooling as it goes. In this way, voids mirror the universe at large, which has cooled from billions of degrees in its infancy to just a few degrees above absolute zero today. The gas that remains inside them is typically warm, hot intergalactic medium, ranging from tens of thousands to millions of Kelvin. Yet paradoxically, the overall thermal environment of a void trends toward the baseline set by the cosmic microwave background. With no nearby galaxies to heat them significantly, with little star formation to inject energy, voids are governed by cosmic expansion more than by local processes. Over time, this makes them colder than the busier filaments that thread the universe together. One of the most studied examples is the so-called Eridanus supervoid, a vast region aligned with a feature in the cosmic microwave background known as the cold spot. Discovered through all-sky maps, the cold spot is an area where the CMB appears slightly cooler than average. For years, its origin was debated. Was it simply a statistical fluctuation, or was it linked to a physical structure in the universe? Observations suggested that the Eridanus supervoid, stretching nearly 1 billion light-years across, could be responsible. Photons passing through the underdense region lose energy due to the integrated Sachs-Wolf effect, producing a cooler signal when they arrive at Earth. This does not mean the void itself is colder in the same sense as the Boomerang Nebula, but it highlights how vast emptiness influences temperature on cosmic scales. Voids thus represent another form of cold. They are not measured in degrees Kelvin like comets or nebulae, but in their lack of energy injection, in the way expansion dilutes both matter and heat. Where galaxies burn bright, voids are silent. Where clusters crackle with hot plasma, voids drift toward the universal background. In this sense, they are the harbingers of the universe's future. For as cosmic expansion continues, the entire cosmos will resemble a growing void, stretched thin, starved of heat, and cooled toward absolute zero. Cosmic voids reveal themselves not through what they contain, but through what they lack. To detect them, astronomers map galaxies across immense regions of space, building three-dimensional catalogues that trace the cosmic web. Surveys such as the Sloan Digital Sky Survey have charted millions of galaxies, and when these maps are plotted, the voids stand out like bubbles between the filaments. They are not absolute vacuums, but their density is so low that their gravitational influence is inverted. Instead of pulling galaxies inward, they allow them to drift outward, expanding the void even further. Over billions of years, matter flows away from these underdense regions toward the denser filaments, leaving the voids emptier still. In this way, voids are dynamic structures, always growing, always deepening, sculpted by the expansion of the universe itself. Temperature in these voids is subtle. The few atoms of gas that linger between galaxies are not especially cold in themselves. They may exist as warm-hot intergalactic medium at tens of thousands of degrees Kelvin, heated long ago by shock waves from structure formation. But because the density is so low, their heat is meaningless on cosmic scales. What defines voids thermally is the absence of energy sources. In clusters and filaments, galaxies inject radiation, stars heat surrounding gas, and black holes spew jets of high-energy particles. In voids, none of this occurs. Radiation is scarce, heating is minimal, and the only pervasive influence is the cosmic microwave background. The background provides a universal floor, and in voids, that floor dominates. Over time, as the universe expands further, voids will cool closer and closer to that baseline, while active regions remain relatively warmer. Thus, the voids are the first places where the cooling of the cosmos becomes apparent. The connection between voids and the cosmic microwave background is most dramatically illustrated by the CMB cold spot. This patch of sky, spanning tens of degrees, shows a temperature slightly lower than the average 2.7 Kelvin. Its discovery in WMAP data, and later confirmation by the Planck satellite, raised immediate questions. Could such a large, coherent cold region be a statistical fluke? Or was it caused by an intervening structure along the line of sight? The Eridanus supervoid, stretching nearly 1 billion light-years, offered an explanation. As CMB photons pass through such an underdense region, they lose energy through the integrated Sachs-Wolf effect, arriving cooler than they would otherwise. While debate continues about whether the void is sufficient to explain the entire cold spot, the case highlights how vast emptiness can imprint itself directly on the oldest light in the universe. Mapping voids also deepens our understanding of cosmic acceleration. By studying how galaxies move around voids, astronomers test the influence of dark energy, the mysterious force driving expansion. Voids expand faster than dense regions, acting like laboratories where the effects of dark energy are magnified. In this way, the cold silence of voids tells us about the future trajectory of the cosmos. They are not just gaps between galaxies, but active players in the cosmic story, shaping the distribution of matter and the flow of energy. Each void is both an absence and a signpost, a place where the cooling of the universe is written into structure. For human imagination, voids are perhaps the starkest representation of cosmic cold. They lack the beauty of glowing nebulae or the drama of dying stars. They are, at first glance, emptiness. Yet their very emptiness is the point. It is within them that we see the fate of expansion, the dilution of heat, the spread of silence. The Boomerang Nebula may win the record for coldest natural temperature, but the voids win in scale. They extend across hundreds of millions of light years, each one a cathedral of stillness, where the background radiation dominates and no new energy is added. They remind us that the universe is not built only of luminous threads, but also of vast, frozen caverns, waiting patiently as the cosmos continues to cool. The study of cosmic voids draws us inevitably toward the future. These vast regions already resemble what the universe will one day become. Empty, silent, governed not by local heating, but by the slow cooling of expansion. In clusters and filaments, stars still burn, black holes still flare, galaxies still collide. But in voids, those dramas are rare. They are previews of the end, quiet expanses, where the only dominant influence is the background radiation left over from the Big Bang. To look into a void is to glimpse the long night that awaits all of space when the engines of galaxies grow cold. The physics behind this trajectory is straightforward, yet profound. As the universe expands, the wavelength of every photon stretches. With each stretch, the energy of the photon drops, and the temperature of the cosmic microwave background falls. Today, it rests at 2.7 Kelvin. In billions of years, it will sink further to fractions of a Kelvin. Stars, meanwhile, will exhaust their fuel, leaving behind remnants that cool across trillions of years. Galaxies will dim, clusters will disperse. What remains will resemble the conditions already found in voids, vast expanses, dominated by near emptiness, with only a faint glow of radiation, marking the memory of a once luminous cosmos. The voids are not just part of the present structure, they are signposts of the universe's destiny. Voids also remind us that cold is not uniform. Just as the cosmic microwave background appears nearly the same across the sky, but contains subtle variations, the temperature of the cosmos is not evenly distributed. Dense regions slow the progress of cooling by generating heat through star formation and black hole activity. Underdense regions accelerate it, emptying faster and allowing background radiation to dominate. Over the long arc of time, the difference matters less, for eventually all regions tend toward the same fate. But today, the contrast helps us see the mechanics of cooling in action. The Eridanus supervoid and the CMB cold spot stand as examples of how structure leaves its fingerprint on temperature. They show us that even in the universal background, the cold is not featureless, but textured, sculpted by the geometry of cosmic matter. For human imagination, contemplating voids is an act of humility. These structures are so vast that our entire galaxy could drift inside one and still be dwarfed by the emptiness surrounding it. They teach us that the cosmos is not primarily galaxies, but gaps between them. They also teach us that cold is not only a matter of degrees, but of absence, of dilution, of expansion itself. In voids, we see cold not as a fleeting extreme, but as a long-term condition, one that grows more dominant with each passing epoch. The Boomerang Nebula may show us how low temperatures can plunge under special conditions, but voids show us what the universe will look like when its fires burn out. Cold is not just a record to be measured, it is the destiny written into the shape of space. As we close this chapter, the narrative points naturally forward, from the Antarctic plateau to comets and icy moons, from molecular clouds to the Boomerang Nebula, and from there to the vastness of cosmic voids. We have traced the hierarchy of cold. Each step has shown us how temperature shapes matter and how extremes reveal truth. But the ultimate question remains: what is the fate of cosmic temperature itself? To answer, we must leave the present behind and journey into the deep future, where thermodynamics governs not nebulae or galaxies, but the universe as a whole. There, in the timescales of trillions and even quintillions of years, the story of cold reaches its final chapter. The journey of cold does not end with nebulae or voids. It extends into the far future of the cosmos itself, a timeline so vast that ordinary numbers struggle to capture it. To understand the fate of temperature in the universe, we must look beyond billions of years into stretches of time measured in trillions and beyond. Thermodynamics, the science that explains the Boomerang Nebula and the cosmic microwave background, also dictates the long destiny of everything. The same laws that govern a laboratory refrigerator or a cloud of expanding gas also govern the universe entire. They tell us that the cosmos, now filled with the warmth of stars and galaxies, is on an inexorable path toward a state of deep cold. Today, the universe is young by cosmic standards. At nearly 14 billion years old, it still blazes with the light of countless stars. Galaxies shine, supernovae explode, black holes accrete matter, and planets circle suns. The background radiation rests at 2.7 Kelvin, cold by our standards, but still glowing faintly in microwaves. Yet this glow is only a remnant of the past, and it is fading. As space expands, every photon stretches, its wavelength lengthening, its energy diminishing. In 100 billion years, the background will cool below 1 Kelvin. In a trillion years, it will fall further, approaching zero in a way that never quite reaches it. The fate of temperature is written in expansion, and expansion has no end. The stars, too, are temporary. Most of those we see today will not endure more than tens of billions of years. Massive stars burn out in mere millions, smaller stars last longer, but all are finite. Red dwarfs, the most common stars in the galaxy, may live for trillions of years, but eventually they too will exhaust their fuel. As each generation of stars dies, fewer are born to replace them. Star formation depends on dense, cold molecular clouds, and these clouds will one day be consumed or dispersed. In time, the galaxy will dim, its once rich spiral arms fading into obscurity. The cosmos will shift from an era of starlight to an era of remnants, when white dwarfs, neutron stars, and black holes dominate. The temperature of interstellar space will continue to fall, with fewer and fewer sources of heat to resist the march toward cold. The physics of this cooling connects to the concept of entropy, the tendency of energy to spread and even out. In a young universe, energy is concentrated in stars, galaxies, and clusters. Radiation flows from hot to cold, from dense to diffuse, sustaining the drama of cosmic evolution. But as time stretches, differences fade, energy spreads thin, heat sources burn out, entropy increases, and the universe approaches equilibrium. That equilibrium is not warmth, but near absolute zero, a state where all differences in temperature are erased. It is sometimes called the heat death of the universe, though it is less fiery than the name suggests. It is instead a cold death, a silence, a state where no free energy remains to drive processes forward. The cosmos, once ablaze, will one day fall into stillness. As the cosmos enters the era of remnants, temperature takes on new meaning. Stars fade, leaving behind white dwarfs, neutron stars, and black holes. White dwarfs, the cooling embers of once sun-like stars, begin their lives searing hot, at over 100,000 degrees Celsius. Yet without fusion to sustain them, they radiate their heat into space, cooling steadily over trillions of years. In time, each white dwarf will dim until it becomes what astronomers call a black dwarf, an object so cold it no longer emits visible light. None yet exist, for the universe is not old enough, but their future is guaranteed. When they do form, their temperatures will fall close to the cosmic background, sinking slowly toward equilibrium as the universe itself grows colder. Neutron stars, born from the collapse of massive stars, follow a similar trajectory. Initially blazing with temperatures of millions of degrees, they too cool by radiating into space. After trillions of years, they will be frigid spheres of degenerate matter, nearly indistinguishable in temperature from their surroundings. Even black holes, those engines of gravity, are not immune. According to Stephen Hawking's theory of radiation, black holes slowly lose mass by emitting particles, an effect so faint that it is negligible today. But across unimaginable spans of time, they too will evaporate, releasing their energy as the last whisper of heat into a cosmos otherwise cold and dark. In this distant future, temperature becomes a universal equalizer, dragging every object toward near absolute zero. The timescales involved defy imagination. Red dwarf stars, the most enduring, may burn for 10 trillion years before fading. White dwarfs will take longer still to cool into black dwarfs, perhaps 100 trillion years. Black holes, especially the supermassive ones at galactic centers, will require even longer to evaporate, up to 10 to the power of 100 years. By then, the universe will be a thin, dark expanse, filled only with elementary particles, drifting in silence. The cosmic microwave background, stretched beyond detectability, will be colder than any thermometer we can conceive. Photons will be so dilute that they scarcely interact. The temperature of the cosmos will hover infinitesimally above absolute zero, asymptotically approaching it but never reaching it, as dictated by the laws of thermodynamics. This vision is sometimes described as the heat death of the universe, but its essence is the dominance of cold. No gradients will remain, no hot and cold regions to drive motion or change. Entropy will reach its maximum, and with it, activity will cease. Cold, which once preserved comets and defined voids, will become the universal state. There will be no boomerang nebula standing apart as colder than the background, no laboratory condensates pushing below nature's floor, no stars to warm their surroundings. The cosmos itself will resemble an infinite void, everywhere the same, everywhere almost absolutely cold. It will be a final equilibrium, the last chapter in the thermodynamic story that began with the blazing fire of the Big Bang. Yet in contemplating this future, we also recognize the scale of the present. The universe is not yet in decline. Stars still shine, galaxies still form, and the cosmic microwave background still glows faintly across the sky. The Boomerang Nebula, though fleeting, is a reminder of extremes that exist here and now, within our observable epoch. Laboratory achievements, though transient, show us that absolute zero remains forever beyond reach, but the path toward it reveals truths about the laws of nature. The fate of temperature is not abstract. It is written in what we see, from Antarctic plateaus to cosmic voids, from laboratory condensates to stellar remnants. Each example is a step along the same trajectory, the long cooling of the universe. In the farthest reaches of time, when stars have cooled, when galaxies have dispersed, and when black holes have evaporated, the universe will stand as an expanse of near absolute stillness. It will not be sudden but gradual, unfolding across timescales so immense that our current age seems like an instant in comparison. Cold will be everywhere, the dominant condition, stretching unbroken across the horizon of reality. No nebula will blaze, no cluster will glow, no furnace of nuclear fire will ignite. Matter itself will be thinned into near nothingness, a sparse gas of particles, adrift in a sea of silence. Thermodynamics dictates this outcome, a slow decline toward maximum entropy, where no differences remain to drive change. In this sense, the destiny of the cosmos is not chaos, but equilibrium, a final resting point, close to absolute zero. To call this the heat death of the universe is to emphasize what will be lost. To call it the cold death is to emphasize what will remain. The record of creation will still be written in faint radiation, stretched into wavelengths beyond imagination. The structures we now see, nebulae, galaxies, clusters, will survive only in memory or in the preserved chemistry of relic particles. Time itself will continue, but events will slow until they are almost indistinguishable from stillness. The universe will not end in a flash, but in a whisper, its temperature hovering forever just above absolute zero, a condition unbroken and eternal. This is the logical conclusion of the same processes we observe in comets, moons, and nebulae. Cold preserves, but cold also forbids. On the largest scale, it preserves the existence of matter, but it forbids further creation. And yet, in contemplating this fate, we find perspective. The universe has not yet reached that silence. We live in an age of light, where stars still form, where galaxies still glow, where the cosmic microwave background still bathes the sky in a faint afterglow of creation. The Boomerang Nebula, discovered by chance in the constellation Centaurus, is a reminder of this fleeting richness. In its brief existence, spanning only a few thousand years, it achieves a condition colder than the cosmic background, a paradox in a universe governed by expansion. For us, it is a glimpse of what will one day come to all things, a cosmos where cold surpasses warmth, where silence surpasses sound. To study it is to study not only a dying star, but also the trajectory of the entire universe. In this sense, the Boomerang Nebula is more than a curiosity. It is a message. It tells us that extremes exist, that the laws of physics can drive matter to states that defy our intuition, yet obey every rule. It tells us that cold is not absence but power, capable of shaping the fate of stars, planets, and galaxies. And it tells us that the ultimate destiny of the universe is written in the same language, the same thermodynamics, that governs its fleeting coldness today. When we look at the boomerang, we are looking at a fragment of the future, scaled down and accelerated, a living demonstration of how expansion cools, how energy disperses, how silence grows. It is, in a sense, a mirror, showing us what lies ahead. The universe began in fire, and it will end in frost. Between those two extremes stretches everything we know: stars, galaxies, planets, life, thought. To understand cold is to understand that trajectory, from the blazing birth to the final stillness. The coldest place in the universe is not simply a record to be noted. It is a story to be understood, a fragment of destiny glimpsed in the present. For now, light still shines, and warmth still fills the galaxies. But the Boomerang Nebula whispers of what will one day be true everywhere, that in the end, all things pass into silence, and that silence is cold.